When you look up at the night sky, you are being lied to. The quiet, peaceful twinkling of stars is a cosmic illusion, hiding a battlefield of unimaginable scale. Out there in the deep dark, black holes are shredding stars, galaxies are actively cannibalizing their neighbors, and invisible halos of dark matter are bending the very fabric of space and time. You are not looking at a silent painting, you are looking at the wreckage and the engines of the universe. So what happens when we leave our cosmic neighborhood and journey across the absolute limits of the known cosmos? We are about to embark on an epic expedition to witness every kind of galaxy in existence. We aren't just going to collect names. We are going to read the true physics of everything written in spirals of fire, rings of young blue stars, and jets of hyper-accelerated plasma. This film is a journey through a cosmic memory that spans billions of years. We will start where gravity turns into catastrophe, watching the antennae and mice galaxies rip each other apart, their collisions forging long tidal tales of bleeding stars. From that chaos, we will drift into the eerily perfect geometries of the universe's visual masterpieces, like the Sombrero Galaxy with its heavy, impenetrable dust lanes, and the baffling Hoag's object, a perfect ring of stars floating around a golden core with absolutely nothing in between. Next, we will descend into the galactic underworld, where distance collapses and ordinary physics breaks down. We'll stand at the edge of active galactic nuclei, like Messier 87 and Centaurus A, watching supermassive black holes fire off relativistic jets that pierce through millions of light years of empty space. But destruction isn't the only extreme. We will also step into violent starburst factories like the Cigar Galaxy and the Cartwheel, where gravitational shock waves trigger the birth of millions of new suns in the blink of a cosmic eye. As our journey pushes further, the light itself will begin to fail us. We will confront the dark and ghostly forms of Dragonfly 44 and Segway 1. Galaxies almost completely devoid of stars, held together by the terrifying invisible grip of dark matter. Then, we will turn our expedition into a time machine, chasing the very first light in the universe to find GNZ11 and JD's GSZ14-0, systems born just moments after the Big Bang. Finally, we will scale upward to the true cosmic giants, monsters like IC1101 and Alcyonius, structures so unfathomably massive that they house trillions of stars and plasma plumes that dwarf our own Milky Way. This is not just a catalog of distant lights. It is a narrative written by gravity, spoken in a dozen different cosmic accents. By the time this journey ends, you will never look at the night sky the same way again. The darkness will no longer be empty. It will be a coherent text of creation, destruction, and survival. Welcome to the ultimate journey to all galaxies in our universe. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From collisions that reshape entire systems, to elegant architectures, to central engines, starburst furnaces, ghostly halos, the edge of time, and cosmic giants. Each stop reveals a different rulebook page, and with every page, the universe becomes less like a mystery to fear and more like a mystery to understand. In the night sky, galaxies look calm, like fixed islands of light suspended in blackness. Yet when we stretch time into motion, They become restless systems, rotating, breathing, and slowly reshaped by encounters that last hundreds of millions of years. This series follows every kind of galaxy we can find, because each one is a clue written in structure, color, and motion. The central question is simple and unsettling because it refuses to stay contained. How do galaxies form, transform, and expose the universe's deepest physics? Collisions sound like instant destruction, but space runs on a different clock and a different scale. Two galaxies can interpenetrate without most stars ever touching, because the typical distance between stars is unimaginably large. Even in a dense, spiral disk, stars are like grains of sand scattered across a continent. The catastrophe is gravitational, not mechanical, and that distinction changes everything we expect to see. Orbits are rewritten, gas is squeezed, and whole disks are pulled into arcs that glow faintly at their edges. What survives is not decided by impact, but by tides, friction, and feedback acting over long, patient intervals. What is born can outshine the old galaxy for a brief, brilliant phase, then fade into a quieter remnant. To understand why collisions matter, we start with a paradox that seems almost philosophical. The universe is mostly empty, yet galaxy encounters are common across cosmic history. Gravity reaches across that emptiness and makes the emptiness irrelevant because it does not need contact to do work. When galaxies pass, every star feels a changing pull, and every gas cloud feels a new pressure gradient. The result is a slow-motion shattering of order that can create a new order, like a storm reorganizing an ocean. If galaxies are ecosystems, then collisions are climate events, rare on a human calendar, inevitable on a cosmic one. Two mergers anchor this chapter because they show the same physics in different poses. The antennae galaxies reveal how tides fling matter outward and ignite starbursts in compressed gas. The mice galaxies reveal how orbital geometry and angular momentum decide the shape, symmetry, and reach of the wreckage. Together, they answer a first, essential question that echoes through every survey image. When galaxies collide, what survives and what is born? The antennae galaxies, NGC 4038 and NGC 4039, are a collision caught mid-act, close enough to study in detail. Their disks have already pierced each other, and their outer regions are stretched into long tidal tails that resemble delicate antennae. In wide field images, those tails arc outward like pale ribbons, fading into the background sky. They are not debris from explosions, and they are not random spray. They are streams of stars and gas pulled outward by differential gravity, where the near side is tugged harder than the far side. The tails trace the encounter's history, like a signature written in starlight and dust. Tidal tails form when gravity steals coherence from a rotating disk, and the theft is precise rather than violent. Material that once followed nearly circular orbits is thrown onto elongated paths because the gravitational field changes faster than the disk can respond. Some of it gains energy and is flung outward, yet it remains bound to the system and will not escape forever. Some of it will later rain back in, feeding the remnant and stirring new waves of star formation. The tails are evidence that galaxies are not rigid bodies with fixed edges. They are swarms of particles responding to a changing gravitational field, each orbit a memory of the encounter. The physics is subtle, but the visual result is unmistakable when we know what to look for. The tails are often rich in neutral hydrogen, a cold reservoir that glows in radio maps even when starlight is faint. Dust lanes thread through the streams, absorbing blue light and reddening the background like smoke in a spotlight. In places, the tails can even host small condensations of gas and stars, hints of tidal dwarf candidates forming from recycled material. These are not new major galaxies, but they are reminders that gravity can assemble as well as dismantle. The same tidal force that stretches a disk can also gather clumps where conditions allow collapse. Inside the antennae, the most important action is not in the tails, dramatic as they appear. It is in the overlap region where gas clouds collide and interpenetrate, because gas is collisional in a way stars are not. Gas cannot pass through itself without consequence, so it compresses, shocks, and dissipates energy. Shocks form as streams of interstellar medium meet at high relative speed, and the temperature can jump before cooling begins. Pressure rises, cooling follows, and dense knots appear where the gas becomes gravitationally unstable. In those knots, gravity wins quickly, and star formation accelerates with astonishing intensity. The overlap region is a laboratory for the basic ingredients of star formation, only turned up to extreme settings. Molecular clouds are squeezed until their internal turbulence can no longer support them against collapse. As the gas cools, it radiates energy away, allowing it to contract further and fragment into cores. The densest pockets become cradles for clusters, not just single stars, because the reservoir is large and the compression is widespread. In optical images, dust can hide the youngest clusters, but infrared light leaks through and reveals their heat. In X-rays, hot gas marks where winds and supernovae have already begun to excavate cavities. These starburst knots are not just pretty clusters sprinkled across a chaotic scene. They are a short-lived phase in galactic evolution when the star formation rate spikes far above normal for the available mass. Massive stars form in large numbers, and they burn hot and fast, living only millions of years. Their ultraviolet light ionizes nearby gas and changes its chemistry, carving bright emission regions around newborn clusters. Their winds carve bubbles and drive turbulence, pushing on surrounding clouds like a continuous blast. Their supernovae inject energy and heavy elements, and they can both trigger and suppress further collapse depending on local conditions. Star formation in mergers is a contest between compression and disruption, and the contest begins almost immediately. Shocks and converging. Flows push gas above the density threshold for collapse, especially where streams collide head-on. Cooling lets the gas shed heat and contract, so gravity can take over and fragment the cloud. Yet the newborn massive stars fight back almost as soon as they ignite, because their radiation and winds couple strongly to dusty gas. Radiation pressure, winds, and supernova blast waves can disperse the same clouds that formed them, tearing apart the nursery. The burst can therefore self-limit, turning a surge of creation into a rapid shutdown. There is also a chemical story unfolding inside these knots, one that connects mergers to the long-term enrichment of galaxies. Supernovae forge heavier elements and seed the surrounding medium with oxygen, silicon, and iron. Over time, those metals cool gas more efficiently, changing how future clouds collapse and fragment. Dust grains grow in enriched environments, and dust reshapes the light we see by absorbing and re-emitting energy. In a merger, mixing is enhanced, and material from different radii is stirred together. The collision, therefore, becomes a mechanism for redistributing not just mass, but composition and future potential. This balance is captured in a practical idea called starburst efficiency, which translates spectacle into measurable physics. It asks how much available gas is converted into stars per unit time during the burst, compared with what the galaxy could do in calmer conditions. In quiet disks, efficiency is modest because turbulence, magnetic fields, and rotation resist collapse. In mergers, efficiency can rise because tides funnel gas inward and shocks compress it beyond ordinary thresholds. But efficiency is never unlimited because feedback injects momentum and heat into the same reservoir. The brightest phase is often the shortest, and the remnant must live with what the burst leaves behind. The antennae show another key truth about collisions, and it is easy to miss if we focus only on the first dramatic pass. Destruction is rarely the final state because gravity keeps working after the initial interpenetration. Tails can fall back, feeding central regions and building new structures from returning material. Gas can lose angular momentum and drift inward, thickening the center and raising the density where star formation becomes easier. Over time, the system trends toward a more spheroidal shape as random motions replace ordered rotation. The merger is not one event. It is a sequence of passes, responses, and settling, each phase leaving a different imprint. Historically, this idea was not always obvious, even to astronomers who mapped the sky with care. Early galaxy classification treated spirals and ellipticals as separate families, as if morphology were destiny. The recognition that interactions could transform one type into another grew with deeper images and with the rise of numerical simulations. When long tidal tails were first studied in detail, they became a turning point because they demanded a gravitational explanation. The antennae, in particular, became an icon of that shift, an image that forced theory to match visible scars. It is a reminder that astronomy advances when structure is treated as evidence, not decoration. To see the geometry more clearly, we turn to the mice galaxies, NGC 46 and 76, which look like two galaxies pulled into motion lines. They appear as a pair with long, thin tails, as if stretched by invisible hands that refuse to let go. Their distorted disks and extended streams reveal the encounter's orbital choreography, frozen into shape at a particular moment. The length and curvature of each tail depend on the angle of approach and the direction of rotation. A prograde encounter, where a disk spins with the orbit, can draw out especially dramatic tails. A retrograde encounter can leave a different, subtler signature, with less extended streams and more internal heating. The mice are valuable because they make a difficult concept visible. Initial conditions matter, and they matter in specific ways. If the orbit is more radial, the encounter is deeper and the disruption is stronger. If the orbit is more tangential, the galaxies can dance longer, exchanging angular momentum over repeated passes. If one disk is tilted, the tails can lift out of the plane, producing warps and asymmetries that persist. Even the mass ratio shapes the outcome, because a smaller companion can be shredded without fully destroying the larger disk. In the mice, the symmetry suggests a relatively comparable pair, but the details still encode the geometry. The mice also show that collisions are about angular momentum transfer, not merely about mixing. As the galaxies pass, tidal torques move angular momentum outward into tails and halos, and that outward transport changes what the inner regions can do. The inner regions can then contract, because they have less rotational support holding them up. Gas responds strongly because it can dissipate energy through shocks and radiation, allowing it to sink inward. Stars respond more cleanly because they conserve energy except for the changing gravitational potential they move through. The visible distortion is therefore a map of where angular momentum went, painted across the sky. Another invisible process shapes the mice and every merger, and it acts like a brake applied to a cosmic orbit. Dynamical friction drags each galaxy through the other's dark matter and stellar background, even when the luminous disks are still separated. The moving mass creates a gravitational wake that pulls backward, stealing orbital energy and angular momentum from the pair. Each pass becomes tighter and slower, and the separation shrinks in a way that is predictable in broad terms. The galaxies do not simply fly apart after the first encounter, because the wake keeps extracting energy. Repeated passages lead to coalescence, and the final remnant can be radically different from either parent. Dark matter is the quiet architect of this whole story, because it supplies most of the mass and most of the gravitational reach. Each galaxy sits inside a massive halo that extends far beyond its luminous disk, where stars are only a thin tracer. When galaxies approach, their halos interact first, long before the bright parts overlap and long before tidal tails become obvious. The halos deepen the gravitational potential and guide the path of the visible collision, shaping the orbit like an unseen landscape. They also absorb and redistribute angular momentum, influencing how quickly the pair will merge and how much material is flung outward. Without dark matter, the tails, timings, and final shapes would not match what we observe. Because dark matter is invisible, we test its role through consequence, using nature's own experiments and our own controlled ones. Computer simulations combine gravity, gas dynamics, star formation recipes, and feedback models, then evolve the system forward in time. By adjusting halo mass, concentration, and gas physics, simulations can reproduce the antennae's tail shapes and the timing of its starburst. They can reproduce the mice's long tails and distorted disks, given the right orbital geometry and viewing angle. When the models match the sky, they do not prove every detail, because subgrid physics is still approximate. They show that the invisible components are constrained by the visible scars, and that constraint is a form of measurement. The comparison between simulation and observation is itself a kind of visual revelation. On one side, a real image shows faint tails, dusty overlap regions, and bright knots of young clusters. On the other, a simulation shows particles and gas streams, colored by density or temperature, evolving into the same broad shapes. When the match works, it tells us the gravitational story is correct in outline, and that the missing mass behaves as a halo. When the match fails, it tells us where our assumptions about cooling, feedback, or initial conditions are incomplete. In that sense, every merger is both a spectacle and a test. These mergers also hint at what happens after the fireworks, when the bright knots fade and the tails thin into the background. Gas driven inward can build a central bulge and change a galaxy's morphology, making the light profile smoother and more centrally concentrated. The same inflow can feed a central black hole, if one is present, and ignite an active nucleus that shines across the electromagnetic spectrum. Feedback from that nucleus can heat or expel gas, further quenching star formation and altering the future supply. Over billions of years, a collision can turn two spirals into a single, smoother system with less obvious memory of its origin. The encounter writes a new evolutionary path, and it can erase much of the original structure. Yet the outcome is not uniform, and that uncertainty is part of the mystery that keeps these systems scientifically alive. Some mergers leave behind elegant ellipticals, while others rebuild disks from remaining gas that settles back into rotation. Some trigger intense starbursts, while others produce only mild enhancement, as if the gas reservoir were reluctant. Some feed black holes efficiently, while others starve them despite the violence around them. The difference lies in mass ratios, gas content, orbital angles, and the hidden architecture of dark matter, which sets the stage for everything else. Collisions are therefore not just dramatic episodes. They are experiments run by the universe, with initial conditions we are learning to read. And there is a deeper question hiding beneath the imagery, one that merges aesthetics with physics. When we see a tidal tail, are we watching matter escape, or are we watching a future stream that will return and rebuild? When we see a starburst knot, are we witnessing a birth that will seed long-lived clusters, or a flare that will blow itself apart? The same physical laws produce both outcomes, depending on timing and environment. In mergers, the universe shows us how sensitive structure can be to history. This chapter reframes the word collision because the word is too small for what is happening. It is not a simple crash of solid objects, and it is not a single moment of contact. It is a gravitational negotiation between vast, rotating ecosystems of stars, gas, dust, and dark matter, each component responding on its own timescale. The visible tails show where matter was flung and where angular momentum was deposited. The starburst knots show where gas was compressed into rapid creation, then challenged by its own newborn stars. The fading of the burst shows how feedback sets limits that no galaxy can ignore. The slow spiral inward shows how friction and halos bring the pair to a final union. From here, the journey widens. If collisions can build bulges, ignite black holes, and reshape entire galaxies, then structure is not a static design. It is a record of forces acting over deep time, written into rings, bars, warps, and asymmetries that persist long after the first pass. Next, we follow the aftermath into stranger forms, where rings, bars, and warped disks become aesthetic masterpieces with physical causes. The question shifts from what collisions do to why the universe produces such varied galactic architecture. We leave Chapter 1 with galaxies torn open, their tidal tails still drifting outward. Now the camera drifts into systems that look deliberate, almost engineered, yet shaped by ordinary physics. The violence has not vanished, but the debris has had time to settle into calmer, legible forms. This shift is not a change in the universe's mood, because gravity never really relaxes its grip. It is a reminder that morphology is information, and symmetry can be as historical as damage. When a galaxy looks balanced, it may simply mean the clock has kept running long enough to smooth the evidence. A galaxy's outline is a compressed archive of forces written in starlight and shadow. Mergers leave scars, accretion leaves subtle twists, and slow internal evolution reshapes disks from the inside. Even the quietest-looking systems carry dynamical fingerprints, if we learn where to look. When we classify galaxies by appearance, we are not sorting decorations for a cosmic gallery. We are reading outcomes of gravity, gas flow, star formation, and time. The familiar categories, spiral, elliptical, lenticular, are shorthand for long histories that do not fit neatly into a single label. Some structures are loud, like tails and bridges that announce a recent collision. Others are quiet, like rings, bulges, and dust lanes that look clean until you ask how they formed. A smooth edge can be the end state of repeated disturbances, not the absence of them. This chapter follows two icons of strange elegance, each famous because it seems too tidy: the Sombrero Galaxy, M104, and Hoag's Object, each a puzzle made from familiar ingredients. They look like exceptions, yet they are built from the same matter and the same equations as every other galaxy. Their beauty is not separate from the central question, because structure is one of the few things the universe shows us directly. How do galaxies form, transform, and reveal deep physics through light and structure? If a galaxy can wear symmetry like a mask, what else might it be hiding behind that polished face? M104 sits close enough to study in detail and distant enough to keep its full context mysterious. It looks like a simple disk with a hat brim, but it is not simple. In wide shots, it reads as a crisp silhouette, while in close-ups it becomes a layered system with competing components. The most immediate feature is the dark lane cutting across the bright body, a line so sharp it feels drawn. That lane is not empty space. It is dust embedded in cold interstellar gas. Against the galaxy's luminous bulge, the lane becomes a stark divider, like ink drawn across a lamp. We see the disk nearly edge-on, so the dust is projected into a sharp band. Geometry turns a thin layer into a dramatic boundary, and projection exaggerates contrast. A modest thickness, stretched across tens of thousands of light years, can look like a blade when viewed from the side. Dust is a small fraction of mass, but it dominates what we see in visible light. Grains absorb and scatter starlight, especially at blue wavelengths where scattering is more efficient. The grains are tiny on human scales, often comparable to smoke particles, yet they reshape the entire appearance of a galaxy. Absorption removes photons from our line of sight, and scattering redirects them into other directions. The result is dimming and reddening that can mimic distance or age, even for nearby regions. A region can look older simply because dust has filtered out the bluer light that would otherwise announce youth. The energy does not vanish, because physics keeps accounts even when our eyes do not. Dust heats up and re-radiates in infrared, shifting the story into wavelengths where the lane becomes a glow. In that longer wave view, the dark cut turns into a luminous tracer, revealing where the cold material is concentrated. That infrared glow is not just a different picture, and it is not merely aesthetic. It is a map of where cold material lives, and cold material is the reservoir for future stars. The infrared also carries temperature information because warmer dust radiates differently than colder dust. In radio wavelengths, cold gas can speak even more plainly through spectral lines. Neutral hydrogen, traced by its 21-centimeter emission, outlines extended disks and warps beyond the visible edge. Molecular gas, inferred through carbon monoxide lines, marks the densest regions where star formation can begin. Gas and dust are coupled to star formation because stars form from dense, cold clouds. Where the lane is thickest, the raw ingredients are concentrated, but concentration alone is not destiny. Inside those clouds, gravity competes with pressure and turbulence, and only the densest pockets collapse into protostars. Yet M104 does not look like a raging starburst, even with so much cold material on display. Its dust is organized, and its star formation is restrained compared with merger systems. The disk feels disciplined, as if the galaxy has fuel in storage but keeps the valves only partly open. That restraint points to another lesson, one that becomes clearer as we compare galaxies. A galaxy can hold fuel without burning it quickly, depending on stability, shear, and how gas is stirred. If differential rotation stretches clouds apart, or if turbulence keeps them puffed up, collapse becomes inefficient even in a gas-rich disk. In spirals, star formation often follows patterns, tracing arms where gas is compressed. In M104, the edge-on view hides much of that pattern, but the physics still applies. The disk rotates, the gas responds, and the dust lane marks where the cold interstellar medium is densest. The sombrero's disk is only half the story, and the other half dominates the frame. The bulge is oversized and luminous, swelling upward above the plane like a bright dome. That glow makes the disk look like a thin brim beneath it, and it changes how we interpret the galaxy's past. Bulges and disks are different dynamical components, and they behave differently under gravity. Disks are rotationally supported and thin, with stars moving on nearly circular orbits. Bulges are hotter systems with more random stellar motions. Disk stars move in organized circles, while bulge stars move in many directions, like a stirred swarm. A large bulge implies a different history than a pure spiral disk, and it narrows the range of plausible origins. It suggests early rapid formation, mergers that heated stars, or long-term internal rearrangement. Each pathway leaves different clues in the ages, compositions, and motions of the stars. In one scenario, the bulge forms early when gas collapses quickly and forms stars fast. The stars become old, metal-rich, and centrally concentrated, because the deepest potential well holds onto enriched material. Rapid star formation also means rapid chemical enrichment, because massive stars live briefly and return heavy elements to the gas. In another scenario, mergers build the bulge by adding stars and scrambling orbits. Even minor mergers can puff up a center over long times, thickening the inner disk and heating stellar motions. A small satellite, repeatedly absorbed, can add stars to the central regions without producing obvious tidal chaos today. A third pathway is secular evolution, where bars and spiral patterns slowly move angular momentum. Gas drifts inward and builds a central concentration over billions of years, sometimes forming a compact, disk-like pseudo-bulge. The process is slow, but it is persistent, and small torques applied for long periods can reshape a galaxy. These pathways can overlap, and M104 may carry pieces of each, layered rather than exclusive. Morphology rarely points to a single cause, but it does constrain the story. The sombrero looks settled, yet its oversized bulge hints that something substantial happened early, or repeatedly, or both. Stellar populations help separate those histories, because stars keep chemical and chronological receipts. Older stars tend to be redder and more metal-rich in massive centers, while younger stars trace recent gas inflow. Spectra add detail that images cannot, because absorption lines reveal temperature, composition, and motion. Metallicity is a fossil of past star formation, and it is measured with surprising precision. More generations of stars enrich the gas, and later stars inherit that chemical signature. Elements like oxygen, magnesium, and iron are forged in stars and supernovae, then mixed into the interstellar medium like dye in water. Even the ratios of elements carry timing information because different supernovae enrich on different schedules. Core collapse supernovae from massive stars appear quickly, boosting alpha elements like oxygen and magnesium. Type Ia supernovae arrive later, adding iron over longer timescales, and the balance hints at how rapidly the bulge formed. The bulge also connects to an invisible engine, one that sits at the center of many galaxies. Massive bulges correlate with massive central black holes, a relationship seen across many galaxies and measured through careful dynamics. The connection is inferred not by a single image, but by stellar velocities that reveal the mass hidden at the center. The correlation is not just a curiosity, because it implies co-evolution that must be explained. If gas funnels inward, it can form stars in the bulge and also feed the black hole, tying their growth to the same inflow. Feedback from an active nucleus can then heat or expel gas, an energy source that can regulate future star formation. In M104, the central black hole is part of the story even when it is not blazing. The galaxy's structure hints at a central mass that shaped inner orbits, tightening the gravitational potential. Close to the center, gravity steepens, orbital speeds rise, and the stellar distribution responds to that deepening well. The sombrero also wears a halo, faint and extended beyond the bright disk and bulge. Halos are where galaxies keep some of their oldest memories, because the outskirts evolve slowly. When the camera pulls back and the exposure deepens, the galaxy stops looking like a single object and starts looking like a system. A halo is not a smooth fog, even when it first appears as a soft glow. It is a sparse population of ancient stars and star clusters, orbiting in a broad, roughly spherical distribution. In the faint outskirts, the light becomes grainy and delicate, and the galaxy's boundary turns from an edge into a gradual fade. Globular clusters are the most useful tracers in that halo, and they have been studied for more than a century. They are dense, long-lived clusters, often older than the disk, and they survive where loose groups dissolve. Each cluster is a compact city of stars, bound tightly enough to persist for most of cosmic time. A rich globular cluster system suggests an active early assembly when conditions favored intense, efficient cluster formation. Clusters can form in violent early episodes, and they can be acquired through accretion of smaller galaxies. When a small galaxy is absorbed, its clusters can survive as identifiable relics, long after its diffuse stars are mixed. Their orbits and metallicities preserve clues about that assembly because clusters do not easily forget. Metal-poor clusters often trace early, primitive star formation, while metal-rich clusters trace later, enriched phases near the center. The distribution of cluster properties can hint at multiple formation epochs, like layers in sedimentary rock. Halos are fossil records because they evolve slowly, and because mixing is incomplete in low-density regions. The low density means fewer interactions and less stirring, so ancient structures can persist for billions of years. In a disk, repeated passages and gravitational interactions stir stars efficiently, but in the halo, the stirring is gentler and incomplete. In the halo, time is stored as motion, and motion can remain coherent. Streams and substructures can persist, revealing past accretion events even when the main galaxy looks settled. a faint arc of stars can be the stretched remains of a satellite, still tracing the orbit it once followed. So, M104 is not simply elegant, and it is not simply a spiral seen from the side. It is layered. A dust-rich disk, a massive bulge, and a halo of ancient stars, each component pointing to different epochs. The disk speaks of ongoing gas physics, the bulge speaks of early concentration, and the halo speaks of assembly by addition. The sombrero teaches a key idea for the rest of the journey, and it is easy to miss at first glance. Clean symmetry does not mean a quiet past. It can mean a past that has had time to settle. A galaxy can be dynamically active and still look composed, because relaxation can erase the obvious mess while preserving deeper signatures. From M104, we move to a galaxy that looks almost impossible, even by the standards of cosmic variety. Hoag's object appears as a near-perfect ring surrounding a compact core with a striking gap between. On screen, it reads like a target, a luminous circle drawn with improbable precision against a dark background. The first temptation is to call it an illusion, because the geometry resembles a known relativistic trick. A ring around a bright center resembles gravitational lensing, where a foreground mass bends background light into arcs. In lensing, geometry and gravity collaborate to create circles and partial rings, and the effect can be spectacularly clean. But Hoag's object is not a simple lens, and the details refuse that easy explanation. The ring and core share the same system, and the colors and structures match a galaxy with internal organization, not a chance alignment. The ring contains star-forming knots that belong to the same object, and the overall configuration behaves like a single galaxy rather than a foreground trick. The mystery is therefore physical, not optical, and it pushes us toward mechanisms rather than coincidences. How does a galaxy make a ring so clean? And why does the space between look empty? If the ring is a place where matter gathered, what mechanism gathered it so neatly, and what prevented the region inside from filling in? Hoag's object forces us back to morphology as history, because rings are rarely accidental. Rings can be signatures of resonances, interactions, or accretion that reorganize gas into narrow zones. A ring is not merely a shape, but a record of how angular momentum and gravity negotiated with dissipative gas. One candidate is a past interaction that disturbed the disk without shredding it, like a bell rung once and left vibrating. A close passage can drive waves through gas, and those waves can pile material into a ring. The encounter does not need to be catastrophic, because even a brief tidal tug can excite long-lived patterns. Another candidate is accretion, where gas arrives with angular momentum that settles into a ring over time. The incoming material can be relatively metal-poor, and it can form stars while the older core remains distinct. If the gas is misaligned or arrives gradually, it can build a structure that looks detached, like a separate component wrapped around the center. A third candidate involves internal dynamics, where a bar or oval distortion once existed and drove resonant structure. Even if the bar fades, the ring can remain as a stellar echo of earlier torques. The disk can remember a past pattern, because gas can be shepherded into a stable radius and then converted into stars that keep the ring visible. To understand rings, we need the physics of density waves, which can organize disks without tearing them. In a rotating disk, gravity and rotation can support wave patterns that move through stars and gas. These waves are not rigid objects, but patterns of enhanced density, like traffic jams that move along a highway even as cars pass through. These patterns create regions where orbits crowd together, and crowding raises density. Higher density makes gas more likely to cool, collapse, and form stars, because cooling becomes efficient when gas can radiate energy away. The stars that form then light up the pattern, turning a subtle dynamical effect into a bright, observable structure. Resonances occur where orbital frequencies match the pattern speed in specific ways, and those radii behave like tuning points. At such locations, the disk responds strongly, and gas can accumulate instead of drifting past. The resonance condition is technical, but the plain idea is simple. Some radii are tuned to the pattern, and the response becomes amplified. When gas accumulates, it does not stay invisible for long, because massive stars announce themselves loudly. It forms massive, short-lived stars that shine blue, making the ring look young and energized. Those bright blue stars are cosmic mayflies, living only millions of years, so their presence means the ring is being refreshed. The core, by contrast, appears yellow because it is dominated by older stars and smoother light. Older populations are redder, and their light is less clumpy because the brightest blue stars have already died. In the core, the glow comes from cooler, longer-lived stars whose combined light looks uniform. This color contrast is a timeline, and it is visible even before we measure a spectrum. The ring marks recent star formation. The core marks earlier formation and long-term stellar aging. The two components look like different chapters of the same story, separated not by distance, but by dynamical history. The gap between them is the most unsettling feature because it breaks our expectation of continuity. It looks like a moat, a region where stars and gas are suppressed, despite being close to both components. The eye expects a bridge of light, yet the galaxy seems to hold a clear boundary, as if something swept the region clean. An empty-looking gap does not require true emptiness, and astronomy often teaches that lesson. It can be a region of low gas density, where star formation drops below visibility, even if stars still orbit there. A population of faint, older stars could be present, but without new star formation, it would not announce itself strongly. Gas can be missing because it was consumed in earlier star formation, removed by feedback, or redistributed by torques into the ring and the center. Gas is dissipative, meaning it can lose energy through radiation and shocks, so it is easier to rearrange than stars. Stars keep their orbits, while gas can be pushed, compressed, and redirected. Gas can also be present but stable against collapse, which is a quieter kind of suppression. Stability depends on rotation, pressure, and self-gravity, and in some regimes, the disk resists fragmentation. In plain terms, the gas can be there, but it can be too warm, too stirred, or too stretched to clump into star-forming clouds. A simplified way to say this is that shear and internal motions can outrun gravity at certain radii. If gas cannot gather into dense clouds, it cannot ignite new stars, and the region stays dim. The galaxy can look quiet not because nothing exists, but because the conditions for collapse are not met. This is the intuition behind Tumray-like stability, a criterion that compares self-gravity to stabilizing forces. When rotation and velocity dispersion are high enough, small perturbations are stretched and dispersed before they collapse. The mathematics is compact, but the idea is familiar. If you keep stirring and stretching a cloud, it struggles to condense. In a ring galaxy, resonances can create a sharp contrast that looks almost artificial. Gas is shepherded into a narrow radius where it becomes unstable, while neighboring radii remain stable and quiet. The result is a bright ring with a dim interior zone, even though the entire system shares the same gravitational field. The gap can also be maintained by orbital structure, because not all orbits support long-lived rings. Some orbit families are stable and supportive of loops, while others are chaotic and less able to hold gas in place. If stable orbit families exist at the ring radius, they can act like rails that guide gas into a persistent circuit. Hoag's object, therefore, becomes a lesson in subtlety, and it challenges our instinct to equate drama with impact. You can get dramatic architecture without a dramatic collision, if the disk's internal clockwork is tuned. The ring looks like a deliberate design, yet it may be the natural outcome of resonance, dissipation, and time. Yet interactions still hover as a possibility because galaxies rarely live in isolation forever. Even a small companion, now gone or absorbed, could have triggered the wave that organized the ring. The universe is full of near misses, and a brief gravitational nudge can leave a long-lived imprint, especially in gas. The broader point is that galaxies are not static arrangements of stars, frozen like ornaments. They are self-gravitating fluids and particle swarms, capable of organizing themselves into patterns. Stars behave like a collisionless population, while gas behaves like a fluid that can shock, cool, and settle. In Chapter 1, we saw chaos made visible through tails and starbursts, and the camera lingered on raw disruption. Here we see order made visible through rings, lanes, and smooth, central light. The contrast is visual, but the underlying physics is continuous, because the same processes can produce either turbulence or symmetry, depending on timing and conditions. Both outcomes come from the same laws, and that continuity is the quiet theme of this chapter. Gravity amplifies differences. Rotation shapes the response. Gas cools and dissipates. Feedback limits what can collapse. A galaxy is always negotiating between accumulation and disruption, and the visible result depends on which side is winning at a given radius. Dust is a recurring actor in this story, and it plays both villain and narrator. In M104, it draws a sharp line through the disk. In ring systems, it can hide young regions and reveal them in infrared. Dust does not merely obscure, because it also traces where dense gas has collected and where star formation is likely to follow. Dust also complicates interpretation because it can mimic age gradients and trick our first impressions. A red region can be old stars, or it can be young stars seen through heavy extinction. Without additional wavelengths, a galaxy can mislead us because color is a mixture of stellar age, composition, and intervening dust. That is why multi-wavelength astronomy matters, and why modern surveys rarely rely on one band alone. Visible light shows where stars shine. Infrared shows where dust re-radiates. Radio shows where cold gas waits. When these views are layered, the galaxy becomes a physical object again, not just a picture, and the missing pieces begin to reappear. Even within visible light, spectra refine the story, turning images into measurements. Absorption lines reveal chemical abundances, and Doppler shifts reveal rotation and dispersion. A galaxy that looks smooth can still be dynamically complex, and a ring that looks static can still be a site of ongoing star formation and gas flow. Stellar populations add another layer of decoding, like reading demographics in light. Blue light traces short-lived massive stars and recent star formation. Yellow and red light trace older, longer-lived stars. The mix is a survey, telling us whether a region is actively forming stars or living on the long glow of older generations. When we combine morphology and population, the galaxy becomes a timeline we can test. The disk shows where gas has been. The bulge shows where early mass concentrated. The halo shows what survived. The ring shows where gas was shepherded into instability. And the gap shows where the conditions for collapse were suppressed. The sombrero's halo and clusters emphasize that galaxies grow by addition as well as by collapse, and that growth can be quiet. Accretion of smaller systems leaves stars in the outskirts, long after the center relaxes. The outskirts are where the universe's slow assembly is easiest to read, because the evidence is not erased as quickly. Hoag's ring emphasizes that galaxies can grow by rearrangement, and that redistribution can be as transformative as new mass. The same material can be moved into a new shape without adding much new matter. Gas can move inward or outward under torques, and when it settles, it can light up a radius with new stars, making a pattern that looks like a separate structure. These are two modes of transformation that keep reappearing across the sky. One is external, through mergers and accretion. The other is internal, through secular evolution and resonant dynamics. Both are powered by gravity, but they leave different signatures, and they operate on different timescales. In real galaxies, both modes often operate together, and the boundaries blur in practice. A minor merger can seed a bar can drive inflow can build a bulge and feed a black hole. The sequence is not guaranteed, but it is plausible, and it is one reason morphology is a record rather than a simple classification. This is why morphology encodes history rather than type, and why the Hubble sequence is a map, not a destiny. A galaxy is not born as a label. It becomes a label after billions of years of processes. The categories we use are snapshots, and the universe is always between snapshots, always evolving. There is also a caution in this beauty, because symmetry can be deceptive. Symmetry can hide complexity, and clean edges can conceal active physics beneath dust and glare. When we see a crisp silhouette, we should ask what the light is failing to show, what is hidden by extinction or washed out by brightness. In M104, the dust lane is a screen that both reveals and hides, depending on how we look. It reveals a cold disk. It hides star formation and any central activity behind extinction. If the nucleus were active, dust could dim it in visible light while leaving its infrared and radio signatures intact. In Hoag's object, the ring is a spotlight on where gas became unstable, and it draws attention away from quieter zones. It hides the regions where stars may exist but do not announce themselves in blue knots. The absence of bright clusters in the gap is not the absence of dynamics, because stars can orbit silently for billions of years. The engines that shape these structures are often invisible in a single image, because light traces only part of the mass. They are in the gravitational potential, in the distribution of dark matter, and in the flows of gas. The light is the tracer, but the mass is the author, and much of that mass does not shine. Dark matter still frames the scene even when we do not mention it, because it sets the stage for rotation. It sets rotation curves, stabilizes disks, and influences where resonances occur. A disk embedded in a massive halo rotates differently than one without, and that difference changes where patterns can persist and where gas can accumulate. The same is true for black holes, which matter even when they are dormant. Even when quiet, they are part of the central mass budget, shaping interstellar orbits and the depth of the potential well. When fed, they can dominate a galaxy's energy output, and the transition can be sudden on cosmic timescales. That possibility changes how we read bulges, because bulges are not only stellar structures. A massive bulge is not only a record of star formation and mergers, it is also a hint of a central black hole capable of awakening. The bulge. Black hole connection invites a question. If the bulge is large, what does that imply about the galaxy's potential for nuclear activity? So the beautiful forms in this chapter are not detours from violence, and they are not a separate, gentler category. They are what violence and time can settle into, and what internal dynamics can sculpt from ordinary matter. A galaxy can be both a ruin and a cathedral, depending on when you look. The universe is not trying to make art, even when the results feel almost intentional. It is running equations, and the solutions sometimes look like design. When a ring forms with startling precision or a dust lane slices a galaxy cleanly, we are seeing the mathematics of gravity rendered in light. As we move forward, the question tightens. If dust can hide a core and bulges correlate with black holes, what happens when the center turns on? What would it look like if the hidden engine stopped idling and began to flood its host with energy? In the next chapter, we follow that hidden engine. We ask how a galaxy's nucleus can become a power source brighter than the galaxy itself, and what that power does to its host. We leave Chapter 2 with dust lanes and bulges reading like calm architecture, shaped by gravity and time, and we carry forward the unsettling idea that beauty can be functional. The same structures that make galaxies beautiful can also become channels, guiding gas inward toward a hidden ignition point. What looks like a decorative spiral arm from afar can, in dynamics, behave like a conveyor, slow, persistent, and difficult to stop. In disks, bars, and spiral patterns, apply steady torques that drain angular momentum from gas. And that loss matters because orbit is a kind of resistance. Gas would prefer to fall straight down the gravitational well, but rotation keeps it suspended like water in a spinning bucket. A bar is especially effective because it is not axis-symmetric, so gravity pulls unevenly, and the gas cannot keep a perfectly circular path. Shocks form along the leading edges of the bar, and the gas dissipates energy there, radiating away heat and settling into tighter orbits. Spiral density waves can do similar work, although more gently and over larger radii. Gas clouds enter a spiral arm, compress, and then leave it, but the arm's gravitational pattern can still exchange angular momentum with the material. Over many rotations, this becomes a slow inward drift, measurable in simulations and inferred from observed gas flows. Even rings, those bright star-forming loops, can mark resonances where inflow stalls, piles up, and then leaks inward again. In mergers, tides and shocks do the same job faster, pushing cold material toward the nucleus. When two galaxies interpenetrate, their gravitational fields tug asymmetrically on each other's disks, and long tidal tails show that angular momentum is being redistributed. Gas clouds collide at high relative speeds, and shocks convert ordered motion into heat, which can then cool radiatively and allow the gas to sink. The process is messy, but the direction is biased toward the center, where the potential is deepest. Inflow is not only a supply line for new stars in the center, and it is not merely a way to brighten a bulge. Inflow can also feed the compact object that waits in many galactic cores. That object is not hypothetical anymore, because stellar orbits and gas dynamics have revealed massive dark centers in galaxy after galaxy. The quiet ones are still there, and the active ones simply announce themselves. Accretion is the key transition from structure to engine, because it turns a geometric rearrangement into a power source. When gas falls inward, gravity becomes a generator, converting potential energy into heat and light. The crucial point is that the energy is released before the final plunge, while matter is still outside the event horizon and still able to radiate. In that sense, a black hole is not a lamp, but it can host a lamp-like process in its immediate neighborhood. An active galactic nucleus begins with a simple imbalance that is almost universal in astrophysics. Matter wants to fall straight in, but angular momentum forces it into orbit, and orbit must be drained before infall can continue. The universe solves this by building a disk, because a disk is where friction-like processes can act for a long time. The disk is not a solid surface, and it is not calm, because gas is a fluid, and it becomes turbulent under shear. The result is an accretion disk, a rotating flow where friction and turbulence turn orbital energy into heat, and where the temperature rises dramatically toward the center. In modern terms, the friction is often magnetic, because weak magnetic fields in a differentially rotating disk can trigger the magnetorotational instability. That instability amplifies magnetic stresses, allowing inner material to lose angular momentum and drift inward, while outer material gains it and moves outward. In plain language, the disk finds a way to trade rotational support for inward motion. The disk radiates across wavelengths, from optical and ultraviolet to X-rays, depending on temperature and opacity, and the spectrum is a map of conditions. Farther out, where the disk is cooler, emission peaks in optical or infrared, and it can resemble a hot blue star field in aggregate. Closer in, temperatures can reach tens of thousands to millions of Kelvin, and the emission shifts into ultraviolet and then X-rays. Above the disk, a tenuous corona of hot electrons can scatter photons to higher energies, adding hard X-ray light that signals extreme conditions. The power source is not nuclear fusion, and it is not a conventional explosion, even though the luminosities can feel explosive. It is the release of gravitational binding energy as matter spirals toward the event horizon. For a black hole, the efficiency can be astonishing, because a significant fraction of rest mass energy can be converted into radiation before infall completes. A typical thin disk around a non-spinning black hole can radiate roughly 6% of the infalling mass energy, and a rapidly spinning hole can yield much more. Per unit mass, accretion can outshine stars by orders of magnitude, and that comparison is not rhetorical. Fusion in stars converts less than 1% of mass into energy over a star's lifetime, and it does so slowly and steadily. Accretion can convert several percent quickly, and it can do it in a compact region where photons can escape efficiently. A galaxy can contain hundreds of billions of stars, yet a fed black hole can dominate the total luminosity. AGN are therefore not a special kind of galaxy, but a phase of a galaxy's life, and that framing changes what we ask. The central question sharpens here, because galaxies reveal deep physics when their cores turn on. How often does this phase occur, and what turns it on or off, and what does it do to everything else? In the long view of cosmic history, activity is not an exception, but a recurring episode. The spectrum of an AGN is broad because multiple regions contribute, and each region has its own geometry and timescale. The inner disk produces intense ultraviolet and X-rays, while dust farther out absorbs and re-emits in infrared. That dust is not a uniform fog, because it can be clumpy and arranged in a thick torus-like structure. When ultraviolet light strikes it, grains heat and glow, and the infrared becomes a kind of thermal echo of hidden power. Gas clouds moving at thousands of kilometers per second imprint broad emission lines, and those lines are more than decoration on a plot. They encode velocities through Doppler broadening, and they encode densities and ionization states through their relative strengths. Narrower lines arise farther out, where velocities are lower and densities differ, and where the gas can be shaped by winds and by the host galaxy's interstellar medium. In some cases, the narrow line region can extend hundreds or thousands of light years, like a faint ionized nebula lit by a central beacon. Some nuclei are obscured by dusty structures that block direct optical views, and this is where the same dust lanes that sculpt galaxies become a veil. Orientation changes what we see, but it does not change the underlying engine, and that insight helped unify many AGN classes. A bright quasar and a dimmer Seyfert can be cousins, separated by accretion rate, mass, and viewing angle. When the line of sight passes through dust, the ultraviolet and optical can disappear, yet the infrared and X-rays can still leak through. The paradox is immediate and persistent, and it has the flavor of a cosmic riddle. How can something that traps light power structures larger than the galaxy itself? The answer is not that light escapes the horizon, because it does not. The answer is that the work is done outside the horizon, where gravity is steep and where magnetic fields can grip plasma like a set of invisible gears. To answer, we descend into two nearby laboratories, where the engine reveals its full reach, and where we can connect theory to images. Messier 87 shows a jet launched from a giant elliptical core. Centaurus A shows a dusty body hiding a feeding nucleus that inflates radio lobes. They are close enough to study in detail, yet extreme enough to make the underlying physics unmistakable. M87 is a massive elliptical galaxy, dominant in the Virgo cluster's central region, and it looks almost serene in visible light. Its smooth starlight hides a dense core where gravity is extreme and the timescales are short. Ellipticals like this are often built through mergers, and their stars move in many directions rather than in a thin disk. That random motion gives the galaxy its rounded shape, but it also means the central potential can be deep and stable. At its center sits a supermassive black hole with a mass of billions of suns, and that number is not merely impressive. Its gravity shapes the orbits of nearby stars and influences the behavior of hot gas in the inner kiloparsecs. In M87, the surrounding environment is rich in hot plasma, because the Virgo cluster is filled with an intra-cluster medium that glows in X-rays. That hot gas is a reservoir, and it can feed the central engine through slow, pressure-driven inflow. We do not see the black hole directly, because the event horizon emits no light, and because there is no surface to shine. we see the consequences of matter and photons moving through curved space-time. Near the horizon, light paths bend so strongly that a photon can loop around the black hole before escaping, and some photons never escape at all. The result is a region of reduced brightness, a shadow, set by geometry rather than by material opacity. The Event Horizon Telescope image is not a photograph of a surface, and it is not a simple snapshot in the everyday sense. It is a measurement of a shadow, a deficit in brightness set by light bending near the horizon. The EHT combines radio telescopes across Earth using very long baseline interferometry, and it reconstructs an image from correlated signals. In effect, the planet becomes a single dish, and the data become a test of whether our equations of gravity match the sky. The bright ring comes from emission in the surrounding plasma, lensed into a near circle by strong gravity, and it is brighter on one side for physical reasons. The plasma is rotating, and relativistic beaming makes the approaching side appear enhanced, while the receding side dims. The ring's size constrains the black hole's mass and tests general relativity in an extreme regime. It also constrains how close the emitting material is to the horizon, and that proximity tells us about accretion physics under intense gravity. This is a new kind of astronomy, built from synchronized radio dishes across Earth, and it rests on timekeeping as much as on optics. Interferometry turns the planet into a virtual telescope, resolving angles as small as tens of micro-arcseconds. That resolution is like reading a newspaper in New York from a cafe in Paris, and it is achieved by recording signals with atomic clocks and then combining them later. The achievement has a history, because decades of radio interferometry paved the way, and the EHT is the culmination of that technical lineage. The result ties a distant galaxy to fundamental physics, and it changes what observing a galaxy can mean. A galaxy becomes a laboratory where space-time curvature is measured, not merely inferred. When the ring matches the predicted scale, it is not just a triumph of imaging. It is a confirmation that, even in the strongest accessible gravity, the same theory still holds. Mass is not only a number in a catalog, because mass sets influence and sets the scale of everything nearby. A more massive black hole deepens the central potential and changes how gas can settle and how quickly it can heat. It also sets characteristic timescales, because orbital periods close to the horizon scale with mass. In a sense, the black hole's mass sets the tempo of the engine, while the gas supply sets the volume. In M87, the black hole is also linked to a structure that extends far beyond the nucleus, and it is visible even in modest telescopes. A relativistic jet emerges from the center and remains collimated over enormous distances. In optical images, the jet appears as a narrow, luminous filament, and in radio, it becomes a broader, structured flow with knots and shocks. That jet is the engine's signature written across space. A jet begins where magnetic fields meet rotating plasma in a deep gravitational well, and where rotation can be converted into directed outflow. The disk and the black hole's spin can twist field lines, building electromagnetic stresses that accelerate particles outward. Close to the launch region, the jet is likely dominated by magnetic energy, and farther out it can convert that energy into particle motion and radiation. The collimation is not accidental, because magnetic fields naturally guide charged particles along ordered paths. In simplified terms, there are two related routes to launch power, and both rely on magnetohydrodynamics rather than on mechanical pushing. One extracts energy from the rotating disk along field lines. The other extracts energy from the black hole's spin through a magnetized horizon. These ideas are known as Blandford, Payne, and Blandford, Zanuck mechanisms, but the core picture is unified. Magnetic fields act like rails, and plasma is flung outward while the system loses rotational energy. The jet is not a beam of ordinary light, even though it can shine brightly at many wavelengths. It is a flow of magnetized plasma, carrying energy as particles and fields, then radiating as it interacts and shocks. Within the jet, instabilities can create bright knots, and collisions between faster and slower portions can form internal shocks. Each knot is a clue, because it marks a site where particles are accelerated again. Relativistic means the bulk flow moves close to light speed, and that phrase has observable consequences. At those speeds, time dilation and aberration matter, and the jet's brightness depends strongly on viewing angle. Even a modest change in orientation can change the apparent luminosity by large factors, because the emission is not isotropic in the observer's frame. This is why some jets dominate the sky as blazars, while others look comparatively quiet. Beaming concentrates emission into a narrow cone, making the approaching side appear brighter, and it can make variability look faster than it truly is. The receding side can look faint or vanish, even if the intrinsic power is similar. This asymmetry is a geometric illusion produced by relativity, but it is also a diagnostic tool. By measuring brightness ratios and apparent speeds, astronomers can estimate the jet's true velocity and orientation. Apparent superluminal motion is a projection effect, not a violation of relativity, and it is one of the most counterintuitive sights in astronomy. A near light-speed blob moving toward us can cross the sky in a way that implies faster-than-light motion, because light travel time compresses the observed interval. The blob does not outrun its own light. Rather, successive photons have less distance to make up as the blob approaches. The sky, in this case, becomes a screen where geometry and timing create an illusion. Across radio to X-ray bands, much of the jet's glow is synchrotron emission, and it is a fingerprint of charged particles in magnetic fields. Electrons spiraling in magnetic fields radiate efficiently, producing a spectrum that carries information about particle energies and field strength. The polarization of synchrotron light can even reveal the magnetic field's orientation, and radio polarimetry turns the jet into a map of ordered and tangled fields. In the highest energy regions, synchrotron can reach X-rays, implying electrons accelerated to extreme energies. Higher energy electrons radiate at higher frequencies and lose energy faster, and this creates a natural clock. That is why X-ray features can mark fresh acceleration sites, while radio can trace older, more extended plasma. A knot that glows in X-rays may fade quickly unless acceleration continues, because the electrons cool rapidly. Radio-emitting electrons can survive longer, allowing the jet's past activity to remain visible like a trail. The jet is therefore a transport system, moving energy from the smallest scales to the largest, and doing so with remarkable efficiency. It connects the event horizon region to the galaxy's halo and beyond. In M87, the jet extends into the surrounding cluster medium, and it does not simply dissipate quietly. It pushes, inflates, and rearranges gas that would otherwise follow gravity inward. This connection leads to feedback, the process that turns a black hole into a regulator. and it is one of the central ideas in modern galaxy evolution. The jet does not merely escape, it pushes back on the environment that feeds it. That pushback can be mechanical, through pressure and shocks, and it can be thermal, through heating and mixing. The result is a coupling between the smallest and largest scales. M87 sits in a cluster filled with hot X-ray emitting gas, and the X-ray images are not smooth. They show cavities and ripples, subtle depressions in brightness where the jet has displaced the plasma. Without heating, that gas would cool, sink inward, and form stars at rates higher than observed. The paradox of clusters is that they contain enough gas to form many stars, yet the centers are often relatively quiescent. Something is preventing the cooling from running away. Jets inject energy into the intracluster medium through shocks, turbulence, and buoyant bubbles, and each pathway leaves a different imprint. They stir and heat the gas, offsetting radiative cooling and preventing a runaway cooling flow. The bubbles rise like hot air in a room, carrying energy outward and mixing the medium. Weak shocks can propagate as sound-like waves, distributing energy more gently across large volumes. This is not a gentle influence, but it is not random destruction either, and that distinction matters. It is a self-adjusting loop where accretion powers jets, and jets alter the conditions for future accretion. If the central gas begins to cool too efficiently, inflow increases and the engine brightens. The resulting jet then heats the gas and reduces the supply, dimming the engine again. An astrophysical thermostat with delays and overshoots. When feedback is strong, it can suppress star formation by keeping gas hot and diffuse, and by preventing dense clouds from forming. When feedback is weak, gas can cool, inflow can rise, and the nucleus can brighten again. The balance is not perfect, and galaxies can swing between states, but the average effect can be stabilizing. This is one reason massive galaxies often have old stellar populations, because their gas was prevented from forming new stars for long periods. The implication reaches beyond M87 because the same physics can operate across the population of galaxies and clusters. Black holes can shape the fate of galaxies, linking central growth to global star formation histories. This link is one reason bulges and black holes correlate across galaxy populations, even though they differ vastly in size. The same inflows that build central stellar mass can also feed the nucleus, and feedback can limit both. Historically, this connection was not obvious because the scales seemed irreconcilable. Early quasar discoveries in the 1960s revealed enormous luminosities from tiny regions, and the energy source was debated intensely. The accretion model eventually won because it matched the required efficiency, and because variability implied small emitting sizes. Later correlations between black hole mass and bulge properties suggested coevolution, and the feedback idea became a bridge between observation and theory. Yet M87 is only one expression of the engine, shaped by an elliptical host and a cluster environment. To see a different pathway to ignition, we turn to Centaurus A. The shift is instructive because the host galaxy is different, the fuel delivery is different, and the obscuration is more dramatic. The engine remains the same in principle, but the surrounding conditions rewrite the visible story. Centaurus A, also known as NGC 5128, looks like a peculiar elliptical or lenticular system cut by a thick dust lane, and it immediately breaks the smooth symmetry we associate with ellipticals. The dust lane is not decoration, but evidence of a past merger with a gas-rich galaxy. In visible light, the lane is a dark slash, textured with filaments and clumps that resemble storm clouds. In infrared, much of that darkness turns luminous because heated dust reveals itself. A merger can deliver cold gas to a system that would otherwise be gas-poor, and it can also deliver it on awkward, misaligned orbits. It can also scramble angular momentum, creating misaligned disks and warped structures that funnel material inward. When the orbital planes do not match, gas streams can collide and dissipate energy, allowing the material to settle deeper. Over time, the galaxy can develop a central disk embedded inside a larger, older stellar body, like a new organ grafted into an ancient host. The dust lane in Centaurus. A signals that cold material survived and settled into the central regions, rather than being completely heated and dispersed. That material can obscure the nucleus in optical light while feeding it steadily. The obscuration is not just a curtain, because it affects which wavelengths escape and which are absorbed. It also shapes our classification, because a hidden nucleus can look modest in visible light while being powerful in X-rays and radio. Centaurus A hosts an active nucleus that shines strongly in radio and high-energy bands, and it has been a cornerstone object in radio astronomy for decades. The core is compact, but its influence is written across the surrounding sky in radio maps. In the southern sky, it is one of the nearest and brightest radio galaxies, and its proximity allows detailed study of jets, knots, and lobes. The galaxy becomes a nearby demonstration of processes that occur across the universe. Here, the engine is partly hidden, but its output is unmistakable, and the contrast between optical and radio is striking. Jets emerge from the nucleus and inflate enormous lobes of radio emission. In some images, the inner jet appears as a bright, narrow feature, while the outer lobes spread like faint wings across a vast region. The scale difference is part of the mystery, because the source is tiny and the consequences are enormous. Radio lobes form when jet plasma pushes into surrounding gas and slows, depositing energy and particles, and the boundary becomes a working surface. The flow creates cavities and cocoons, bounded by pressure and shaped by the external medium. Where the jet terminates, it can form hotspots, regions of compression and particle acceleration. The lobe then expands, buoyant and overpressured, and it can rise through the surrounding halo gas. The lobes can extend hundreds of thousands to millions of light years from the galaxy, and their faintness hides their immensity. Their size is a time record, integrating jet power over millions of years. If the jet power changes, the lobes do not respond instantly, because they store energy like a charged capacitor. In that way, the radio sky preserves a memory of activity that may no longer be obvious in the core. Inside the lobes, magnetic fields and relativistic particles store energy, and that stored energy is not trivial. Cosmic rays, mostly protons and electrons, can persist long after the central engine changes state. The particles can diffuse, the fields can tangle, and the emission can fade, but the energy remains in altered gas dynamics. Even when the lobes become ghosts, they can still influence how hot gas moves and cools. Radio observations reveal these structures because synchrotron emission is efficient at long wavelengths, and because the lobes are dominated by non-thermal processes. Optical images can miss the lobes entirely because the plasma is tenuous and does not shine like stars. The radio sky therefore adds a second anatomy to galaxies. It shows where energy went, not where starlight is concentrated. Centaurus A demonstrates how mergers feed AGN in practice, and it does so with a clarity that is almost diagrammatic. A collision brings gas, dust obscures the center, and inflow builds an accretion disk that powers jets. The merger also leaves shells and ripples in the stellar distribution, subtle arcs that hint at past disruption. The galaxy's present appearance is a fossil record, and the nucleus is the active chapter still being written. It also shows that feedback is not limited to clusters like Virgo, and that a jet does not need a rich intracluster medium to matter. Even in a less massive environment, jets can heat gas, disturb the interstellar medium, and alter future star formation. The interaction can carve channels through dense gas, and it can drive turbulence that changes cloud lifetimes. In some cases, the jet can couple strongly to molecular gas, the very material that would otherwise form stars. In some regions, jet interaction can compress gas and trigger localized star formation, and this complicates the narrative of quenching. In other regions, it can shred clouds and prevent collapse, depending on density and geometry. A dense cloud hit obliquely may be compressed at its edge, while a diffuse region may be evacuated. The outcome depends on pressure balance, cooling time, and the jet's stability as it propagates. The details differ, but the theme is consistent, and it returns us to scale. The nucleus is small, yet it can restructure gas on galactic scales. That restructuring can be subtle, like a change in temperature and entropy, or dramatic, like a cavity blown in hot gas. Either way, the galaxy's future star formation is being negotiated by a compact engine. This returns us to the chapter's central tension, and it becomes sharper the longer we look. The event horizon is smaller than a solar system, yet the lobes can span volumes larger than the entire host galaxy. How does a region so small reach so far? And why does the surrounding matter respond so strongly? The answer is not in size, but in energy density and in the ability to deliver energy without losing it quickly. The resolution lies in efficiency and leverage, and both are physical rather than metaphorical. Accretion converts mass to energy with high efficiency, and jets deliver that energy with low radiative loss over long distances. A jet can remain collimated because magnetic fields and pressure gradients guide it, and because relativistic inertia helps it punch through surrounding gas. The energy arrives far from the center, still capable of doing work, heating, lifting, and stirring. Gravity supplies the budget, magnetic fields provide the coupling, and plasma carries the work outward, and these roles are distinct. Gravity releases energy as matter falls inward, and that energy can appear as radiation or as mechanical power. Magnetic fields organize the flow and can tap rotation, turning chaotic motion into a directed outflow. Plasma, being charged, responds to those fields and becomes the vehicle that exports the energy. Active nuclei also remind us that the universe's story is written across wavelengths, and that no single band is enough. What looks quiet in visible light can be loud in radio, infrared, or X-rays, and that mismatch is a clue rather than a problem. Dust can hide ultraviolet and optical emission, but it cannot hide the infrared glow of its own heating. Hot gas can be invisible in optical light, yet bright in X-rays, and jets can be faint in stars, yet vivid in radio. This multi-wavelength truth loops back to the opening hook of the series because it changes what we think we are seeing. The points of light we see are only a fraction of what is happening, because much of the action is hidden in dust and revealed in non-optical bands. When we overlay radio contours on an optical image, the galaxy gains a second skeleton, one made of fields and particles. The familiar starlight becomes only the surface layer of a deeper, more energetic system. AGN are therefore both destructive and creative in consequence, and the balance can shift with environment and time. They can quench star formation by heating gas, yet they can also redistribute metals and energy, shaping the conditions for later growth. Outflows can carry enriched material into halos, seeding future generations of gas with heavier elements. They can also regulate how quickly gas recycles back into the disk, changing the cadence of star formation. They also connect galaxies to fundamental physics in a direct way, and this connection is unusually concrete. The EHT shadow tests spacetime, and jet synchrotron emission tests particle acceleration and magnetohydrodynamics. The same object that curves light also accelerates electrons to energies far beyond any chemical process. In that sense, a galaxy's core becomes a natural experiment, running continuously and broadcasting its results across the electromagnetic spectrum. In this chapter, galaxies stop being only stellar systems and become engines, and the shift is conceptual as much as observational. They transform gravitational potential into radiation, and they export that power into their surroundings. The engine's on and off states become part of galactic evolution, and they leave signatures that can persist long after the core dims. Lobes, cavities, and heated gas can outlast the flare that created them. A galaxy can spend long periods quiet, then flare when inflow rises, then quiet again when feedback starves the core, and this rhythm may repeat many times. The cycle is driven by supply and by angular momentum transport, and those are shaped by structure. Bars, spirals, and mergers can open the valves, while jets and winds can close them. The galaxy's visible shape is therefore not just an outcome of gravity, but a control system for its own central engine. M87 shows the cleanest measurement of a black hole's shadow and a jet that reaches into a cluster atmosphere, and it anchors the story in precision. Centaurus A shows a dusty merger remnant where the core feeds behind a veil and inflates giant radio lobes, and it anchors the story in texture. Together they answer the paradox in operational terms. A light-trapping object can still power vast structures because the energy is released before matter crosses the horizon. The last step is to widen the frame again, because black holes are not the only way galaxies expel energy and matter, and the cosmos rarely relies on a single mechanism. The next chapter follows another engine, driven by star formation itself. Starbursts can launch galaxy-scale winds, carrying gas, dust, and metals into halos and beyond. The question remains the same, but the mechanism changes, and the universe offers another solution. We move forward with a sharpened sense of scale and with a quieter kind of awe. In the smallest regions, gravity writes its most extreme equations, and it does so with magnetic fields as punctuation, tight, forceful, and precise. In the largest structures, galaxies carry the consequences, and the autobiography continues, written in radio lobes, X-ray cavities, and the faint infrared glow of hidden fire. We leave Chapter 3 with black holes acting like thermostats, regulating galaxies through accretion-powered jets and winds. Now we pivot to a second engine that can rival that reach, powered by stars themselves. It is less exotic than an event horizon, yet it can still reorganize a galaxy's future. AGN feedback burns fuel by accretion, converting gravity into radiation and mechanical force near an event horizon. Stellar feedback burns fuel by star formation, converting cold gas into short-lived massive stars and supernovae. The fuels differ, but the consequences can converge at galaxy scale, especially when gas is plentiful and densely packed. Accretion concentrates energy into a tiny region, and it can couple outward through jets, winds, and radiation pressure. Star formation spreads energy across clusters and associations, and it couples outward through shocks, turbulence, and expanding bubbles. Both processes turn a galaxy's gas into a responsive medium, heated, stirred, and sometimes expelled. Both engines can heat gas, drive outflows, and reshape future star formation across kiloparsecs. Both can enrich halos with metals, and both can starve their hosts by removing fuel. The mystery is not which engine is stronger, but when each dominates, and why the balance shifts across cosmic time. One reason the comparison is so revealing is that the coupling problem is the same in both cases. Energy is easy to generate, but it is hard to deliver efficiently into cold, clumpy gas. A jet can drill through a halo and miss the disk, while supernova energy can radiate away if it is injected into dense clouds. So the real question becomes practical and physical. How does energy find leverage in a messy galaxy? A starburst is not just a bright galaxy, and it is not defined by beauty or chaos. It is defined by star formation rate per unit stellar mass far above the normal main sequence. In practice, it means a galaxy is converting gas into stars with extreme efficiency, often in a compact region where pressures and densities are unusually high. The main sequence is an empirical baseline discovered as surveys mapped star formation across thousands of galaxies. Most star-forming galaxies fall along a tight relation between stellar mass and star formation rate, as if they follow a steady metabolic pace. A starburst is a departure from that pace, an episode where the galaxy sprints, burning through its reservoir faster than its long-term average would allow. That definition matters because brightness can lie, while efficiency is harder to fake. A massive galaxy can be luminous without being unusual, simply because it contains many stars already. A smaller galaxy can appear modest in total light, yet still be in a true burst if it is forming stars at a furious rate for its size. In physical terms, the burst is often described by a short depletion time, the time required to exhaust the available gas. Normal disks can take billions of years to use their molecular reservoirs, even while forming stars steadily. In a compact burst, the depletion time can fall to tens or hundreds of millions of years, fast enough to feel like a crisis in the galaxy's budget. To measure a starburst, we do not rely on one wavelength, because dust and geometry can mislead. We combine tracers that respond to young stars, ionized gas, dust heating, and the deaths of massive stars. The goal is to reconstruct the same physical story from different angles, then check whether the pieces agree. H-alpha emission marks ionized hydrogen around hot, young O and B stars. Those stars emit ultraviolet photons energetic enough to strip electrons from hydrogen, and the recombination glow produces the familiar red line. Because the most massive stars live only a few million years, H-alpha is a near instantaneous indicator of very recent star formation. But H-alpha also carries a warning label because dust can absorb it, and because the line depends on the escape of ionizing photons. In crowded starbursts, some ultraviolet light is trapped inside dense regions, and the H-alpha we observe can undercount the true activity. Astronomers correct for this with line ratios and extinction estimates, careful bookkeeping hidden behind a simple red glow. Ultraviolet light traces the same massive stars directly, but it is easily absorbed by dust. In a clean environment, UV maps can look like a blueprint of star-forming regions, sharp and structured. In a dusty starburst, much of that UV never escapes, and what we see can be only the outer skin of a much larger hidden engine. Infrared emission traces dust heated by starlight, often revealing hidden star formation. Dust grains absorb ultraviolet and optical photons, then re-radiate the energy as warm infrared glow. In the most compact bursts, the infrared can dominate the galaxy's luminosity, turning the system into a furnace that shines brightest where visible light is most suppressed. The infrared is especially powerful because it behaves like a calorimeter for young stars. If dust is thick enough, it captures most of the ultraviolet output and re-radiates it, letting us infer the star formation rate from total infrared luminosity. Yet even here, geometry matters. Dust can be heated by older stars too, so astronomers compare bands and temperatures to isolate the burst. Radio and X-ray observations add the aftermath, because supernova remnants accelerate particles and heat gas. Non-thermal radio emission traces cosmic rays spiraling in magnetic fields, and it can persist after the brightest stars have died. X-rays trace hot plasma from shocks and superbubbles, a signature of mechanical energy that has been thermalized into million-degree gas. Radio measurements also exploit a remarkable empirical link, the far infrared. Radio correlation, which ties dust heating to cosmic ray production. That correlation is not a law of nature, but it is a clue that star formation couples to magnetic fields and particle acceleration in a repeatable way. In a starburst, deviations from the correlation can signal unusual conditions, stronger fields, faster losses, or an embedded AGN. Together, these bands separate star formation from AGN when both can coexist. An AGN can mimic some tracers, especially in X-rays and infrared, but the spatial patterns and spectral fingerprints differ. Star formation tends to appear clumpy and distributed across regions of gas, while an AGN often concentrates power toward the nucleus, though nature enjoys exceptions that keep observers cautious. Multi-wavelength work also forces a deeper question. What do we really mean by rate in a chaotic system? Each tracer averages over a different timescale, from a few million years to tens of millions. A galaxy can therefore look inconsistent if it is rapidly rising or fading, and that inconsistency itself becomes a clue about the burst's timing. In other words, a starburst has a light curve, even if we cannot watch it unfold in real time. A mismatch between ultraviolet and infrared can imply that dust is changing, or that the burst is aging. A weak H-alpha signal alongside strong radio can mean the most massive stars have already died, leaving supernovae as the lingering echo. Starbursts are brief compared with a galaxy's age, because they consume and disrupt their own fuel. They are often triggered by interactions that compress gas and drive inflows. They are also regulated by feedback that can both stimulate and suppress collapse, as if the galaxy is trying to run and break at the same time. In simulations, A burst can ignite when gas loses angular momentum and piles into the center, raising density until gravity overwhelms support. In observations, we see hints of that process in disturbed morphologies, tidal tails, and warped disks. The burst is therefore not only a stellar event, but also a dynamical one, an outcome of gravity rearranging the gas supply. Angular momentum is the quiet gatekeeper in this story. Gas in a rotating disk wants to stay in orbit, and it must shed that rotational support to fall inward. Tidal torques from a companion, shocks in a bar-like distortion, and cloud-cloud collisions can all drain angular momentum, slowly at first, then suddenly when the disk is strongly disturbed. We follow this engine into the nearby M81 group, where gravity links several galaxies in a slow dance. In that environment sits Messier 82, the Cigar Galaxy, a compact starburst shaped by interaction. Even in small telescopes, it looks like a bruised ember, elongated and mottled, as if something has squeezed it from the sides. M82 is not isolated, and its current state is not an internal accident. Tidal forces from its massive neighbor M81 and the broader group potential have disturbed its disk and redistributed angular momentum. The interaction has driven gas inward toward the central regions, turning a once more ordinary disk into a concentrated star-forming core. The history of M82's recognition is a reminder of how perspective changes with technology. Early photographs showed a peculiar dusty galaxy, but the true scale of its activity emerged with infrared and radio astronomy. As instruments improved, the cigar became a laboratory, close enough to resolve structure, violent enough to expose the physics. By the late 20th century, M82 helped define what a starburst even looked like in practice. Radio maps revealed compact sources associated with supernova remnants, like a city skyline of explosions frozen in time. Infrared measurements showed that dust, not starlight, carried much of the luminosity, an early hint that galaxies can hide their power behind soot. Gas inflow matters because star formation requires dense, cold clouds that can collapse. Tidal torques and shocks can pile gas into the inner kiloparsec, raising pressure and collision rates between clouds. The center becomes a factory line where gas is processed quickly and where the usual balance between collapse and support is tilted toward runaway formation. In calmer disks, clouds form stars inefficiently, partly because turbulence, magnetic fields, and shear resist collapse. In M82's core, those supports are overwhelmed by crowding and compression, and the gas surface density climbs. When gas becomes that concentrated, even small perturbations can trigger collapse, and the star formation becomes clustered by necessity. At these densities, the interstellar medium changes character. Molecular gas becomes more volume-filling, temperatures and cosmic ray densities rise, and the pressure can exceed what the Milky Way experiences by orders of magnitude. The result is a different regime of star formation, still governed by gravity, but operating inside an environment that is hotter, noisier, and more extreme. The star formation rate rises far above what M82's mass would predict for a calm disk. Massive clusters form, and the stellar population becomes dominated by short-lived, luminous stars. The burst is intense enough that it changes the galaxy's energy budget, so that mechanical power begins to compete with gravity on large scales. Visually, the central region is a bright knot wrapped in dark lanes, with dust cutting across the light like ink. In infrared maps, the dust glows instead of obscuring, outlining where energy is being absorbed and re-emitted. In optical images, The disk looks shredded, and the eye is drawn to the vertical plumes that hint at something escaping. If we could fly through the core, we would see star formation packed into a region only a few hundred parsecs across. Clusters would be embedded in cocoons of gas and dust, their ultraviolet light carving cavities and ionized skins. The scene would feel industrial, bright, crowded, and turbulent, like a furnace room inside a galaxy. Yet the most important product is not only starlight, but mechanical power injected into the interstellar medium. Massive stars drive winds during their lives, and they explode as core collapse supernovae within a few million years. In a concentrated region, those inputs overlap and reinforce, creating a collective effect that no single star could achieve. A single supernova releases about 10 Hubble 51 ergs of energy, but what matters is how much couples to the surrounding gas. In a dense environment, radiative losses can be severe, yet clustering changes the outcome. Multiple explosions carve a shared cavity, lowering density, reducing cooling, and allowing more energy to remain as pressure. This is why starbursts behave differently from scattered star formation across a disk. When supernovae occur in isolation, their remnants stall as they cool, and much of the energy is lost as radiation. In a starburst, the remnants overlap before they fade, building a coherent superbubble whose interior stays hot and overpressurized. The combined winds and supernovae create an overpressurized hot cavity in the central starburst. Hot gas expands, and when it finds a path of least resistance, it vents outward. In a disk galaxy, that path often aligns with the minor axis, where the density drops fastest and where the disk's layered structure offers seams to pry open. This is the birth of a super bubble that grows until it breaks out of the disk. The breakout is not gentle, and it can resemble a blowtorch punching through a thin roof. Once the hot gas reaches lower density halo material, it accelerates, and the outflow becomes a sustained wind rather than a confined bubble. Breakout also changes the efficiency of feedback in a subtle way. While the bubble is trapped, it does work on dense gas and can compress shells, but it also suffers strong cooling at its boundaries. Once it vents, the hot gas can escape more freely, carrying energy and metals outward, yet it may couple less to the remaining disk, leaving behind a scarred but still star-forming core. M82 launches a superwind, a galaxy-scale outflow driven by stellar feedback rather than a black hole. It is not a single phase of gas, and it is not a clean chimney. It is a multi-phase flow where different temperatures and densities coexist, braided together by turbulence and threaded by magnetic fields. At the hottest end, X-ray observations reveal plasma at millions of degrees, produced by shocks and thermalized supernova energy. This hot component carries much of the pressure and can escape most easily. It is the core driver that pushes on everything else, and it sets the wind's overall momentum budget. In X-ray images, the outflow appears as a soft, elongated glow extending above and below the disk. The emission traces regions where the gas is dense enough to radiate, not necessarily where most of the mass resides. That distinction matters. Some of the most influential gas can be nearly invisible because low-density plasma carries energy efficiently while emitting weakly. Warm ionized gas forms filaments and shells, visible in optical emission lines like H-alpha. These structures trace interfaces where hot gas meets cooler material and where shocks and radiation keep gas ionized. They also map the wind's geometry and its interaction with the disk, creating a skeletal outline of the outflow's shape. Those filaments look like luminous threads pulled taut, rising in arcs and streamers that suggest both order and violence. Some appear as limb-brightened walls of expanding cones, hinting at hollow cavities inside. Others break into knots and curls, where instabilities wrinkle the flow and where dense clumps resist being torn apart. If we watch the filaments in our mind's eye, they feel like weather in fast motion. Hot gas surges upward, cool gas peels away, and the boundary between them flickers with shocks. The wind's shape is not fixed. It breathes, narrows, and broadens, because the starburst itself is not steady on short timescales. Cold gas is not absent, and that is a crucial clue about how winds work. Molecular gas can be entrained and lifted, and neutral material can be accelerated in clumps. The wind becomes a conveyor that can carry the raw, star-forming fuel out of the galaxy, even while other parts of the gas remain behind. This cold component is difficult to move because it is heavy and easily fragmented, yet observations show it participating anyway. The likely mechanism is not simple pushing, but a combination of ram pressure, turbulent mixing, and magnetic draping around clouds. The result is messy. Some cold gas survives as coherent clumps, while some is shredded into mist that mixes into warmer phases. The multi-phase structure implies that feedback is not a simple heating event. It is a complex coupling between hot plasma, magnetic fields, turbulence, and dense clouds. Some clouds are shredded and mixed, while others survive long enough to be accelerated outward, depending on their density contrast, size, and the wind's velocity. The physics at the interfaces is where much of the uncertainty lives. Thermal conduction can evaporate cloud surfaces, while radiative cooling can allow mixed gas to condense again. Instabilities can tear clouds apart, yet rapid cooling can also create new cold fragments. So the wind can destroy and create structure simultaneously. These interfaces are also where the wind's momentum is translated into visible forms. A hot flow can slip past a cloud, but the shear layer between them becomes turbulent, thickening into a mixing zone. In that zone, energy cascades down to smaller scales, and cooling can light up the gas, turning invisible dynamics into observable filaments. The superwind is also a chemical engine, because starbursts are efficient forges of heavy elements. Massive stars synthesize oxygen, carbon, silicon, and other metals, then return them through winds and supernova ejecta. The burst enriches the surrounding gas on short timescales, turning stellar evolution into a rapid chemical experiment. Historically, the realization that galaxies recycle elements was a conceptual turning point. Early astronomy treated stars as fixed lights, but spectroscopy revealed changing compositions and evolving populations. Starbursts make that evolution visible in real time because they produce and distribute metals so quickly that the surrounding gas can measurably change within a single burst episode. In the 20th century, the language of metals became a bridge between stellar physics and cosmology. It reminded astronomers that the early universe began almost chemically simple, dominated by hydrogen and helium. Every oxygen atom in a starburst wind is therefore a historical record, proof that generations of stars lived, died, and altered the cosmic inventory. When enriched material is carried into the halo, it changes the circumgalactic medium that surrounds the galaxy. Metals increase cooling efficiency, alter dust content and seed future accretion with heavier elements. Later generations of stars and planets become metal-rich because earlier bursts exported and recycled these products, and because the galaxy's environment becomes progressively more chemically complex. The halo is not empty space, even if it looks dark in ordinary images. It is a tenuous atmosphere of ionized gas, threaded with inflows and outflows, and it acts as the galaxy's long-term reservoir. When a wind injects metals into that reservoir, it changes how easily gas can cool and return, and it changes the composition of whatever later condenses into new clouds. This is where the central question sharpens again, because feedback is a bridge from small-scale physics to cosmic structure. How do galaxies transform, and how do they reveal deep physics through light and motion? In M82, we see that stellar evolution can regulate a galaxy as effectively as an AGN, even without a central black hole dominating the energy budget. The tension is built into the mechanism because the burst both creates and destroys its own conditions. Star formation builds the ingredients for planets and life, but it also generates the forces that can end the burst. The same massive stars that light the factory can blow the factory apart, and the timescale is brutally short by galactic standards. Self-regulation begins with energy and momentum injection into the gas reservoir. Heating raises pressure and can prevent collapse, while bulk outflow removes mass entirely. If enough gas is expelled or kept hot, the star formation rate must fall because the raw material is either gone or no longer able to fragment. Momentum matters as much as energy because even strongly cooling gas can still be pushed. Radiation pressure on dust, stellar winds, and supernova blast waves all deliver momentum that can accelerate clouds. In a dense starburst, these contributions overlap, and the cumulative push can exceed the gravitational pull holding gas in the disk. There is a subtlety here that observers wrestle with. A wind can be fast without being massive, or massive without being fast. What matters for long-term evolution is the mass loading, how much cold and warm gas is carried along per unit star formation. High mass loading can starve a galaxy quickly. Low mass loading can vent energy while leaving most fuel behind. But feedback is not only suppression, and the evidence is written in the wind's edges. Expanding shells can compress surrounding gas, raising density and triggering new star formation at interfaces. Creation and quenching are intertwined, and the net outcome depends on geometry and timing, whether compression wins before heating and disruption take over. On the rims of bubbles, gas can be swept into thin, dense layers where gravitational instability becomes easier. This collect and collapse process can produce arcs of young stars, like beads on a string. The same wind that empties the center can therefore seed activity farther out, shifting star formation rather than simply extinguishing it. It invites an uncomfortable question about cause and effect. When we see young stars on a shell, are we watching feedback trigger new birth, or are we seeing star formation that would have happened anyway, merely rearranged into a visible pattern? The difference matters because it decides whether feedback is mostly a break, mostly a sculptor, or both at once. In M82, the starburst likely cannot last long at its current intensity. Gas consumption times are short, and outflow rates can rival or exceed the star formation rate. The burst is therefore a phase, not a permanent identity, and it will fade unless new gas arrives, either from the halo or from future interactions. We can frame this as a budget. How much gas enters the central region, how much becomes stars, and how much is expelled. If the expulsion term dominates for long, the center empties, and the burst collapses under its own success. If inflow keeps pace, the burst can persist longer, but it risks building an even stronger wind that eventually breaks the balance. That return of gas can happen through recycling, because not all outflow escapes. Some material slows, cools, and falls back in a galactic fountain. The galaxy becomes a loop where gas cycles between disk and halo, carrying metals and turbulence with it, and the loop can repeat across multiple episodes. A fountain is not a failure of feedback, but a different mode of regulation. Gas launched upward can mix with the halo, cool, and rain back down at different radii, redistributing angular momentum. In that way, feedback can reshape a disk's structure, even when it does not permanently remove mass from the system. This loop echoes the AGN thermostat from Chapter 3, but with different physics and different scales of energy release. Black holes inject energy from deep gravitational wells, while starbursts inject it from clustered stellar deaths. Both can maintain a dynamic equilibrium, and both can overshoot into quenching, leaving a galaxy temporarily quiet and gas-poor. The comparison invites a subtle observation. The universe has multiple ways to regulate itself, and it often uses more than one at once. In some galaxies, an AGN and a starburst coexist, each complicating the other's signatures. When we see an outflow, we must ask what is driving it and whether the driver changes over time. To see a different trigger, we leave the M81 group and travel to a galaxy that looks like a diagram of impact. The Cartwheel Galaxy presents a bullseye structure that demands an explanation in dynamics. Its outer ring shines with young stars, while the interior looks strangely hollow, as if something has swept the disk clean. The cartwheel is not a typical spiral with arms, and it is not a stable resonance ring like some barred galaxies. Its morphology suggests a transient wave moving through a disk. The most successful model is a direct collision that punched through the target galaxy, leaving behind a propagating disturbance rather than a permanent pattern. Ring galaxies have a history in astronomy that mirrors the broader shift toward dynamical thinking. Early classifications treated morphology as a static label, but peculiar systems forced new explanations. The cartwheel became iconic because it looks so geometric, yet the geometry is the imprint of a violent, fleeting event. In the collisional ring scenario, a smaller intruder passes nearly head-on through the disk of a larger galaxy. The stars mostly pass by without direct collisions, but the gravitational disturbance is sudden. The disk responds by launching a radially propagating density wave, an organized response of many orbits to a single impulse. The wave behaves like ripples in a pond, but the medium is a rotating, self-gravitating disk. Orbits are perturbed, and material piles up at the wave front. Gas, being dissipative, shocks and compresses more strongly than stars, and it can radiate away energy, allowing it to collapse rather than simply oscillate. In visuals, we can imagine the disk as a sheet of faint starlight, then watch a ring brighten as the wave moves outward. The ring is not a solid object traveling through space, but a location where conditions briefly become extreme. Behind it, the disk relaxes, and the stellar populations begin to age, shifting color as the hottest stars disappear. Where gas is compressed, cooling becomes efficient, and clouds collapse into new stars. The result is a bright ring dominated by young blue clusters and H2 regions. The ring is therefore not just a shape, but a moving site of star formation, sweeping outward like a lit fuse across the disk. The physics of compression is straightforward in principle, yet dramatic in consequence. As gas density rises, radiative cooling increases, allowing the gas to shed heat and become even denser. That runaway can tip regions into gravitational collapse, and the outcome is a burst of star formation that traces the ring with startling clarity. The cartwheel's ring marks a timeline because its radius encodes how long ago the collision occurred. As the wave propagates outward, the star formation front moves with it. Inner regions can age and redden after the wave passes, leaving an older interior behind, while the rim remains youthful and luminous. This is why ring galaxies are so valuable. They separate cause and effect in space. The trigger is localized to a moving front, and the aftermath is left behind like a wake. By measuring stellar ages and gas properties at different radii, we can reconstruct the sequence of events with unusual confidence. Timescales are long by human standards, but short by galactic standards. Ring expansion can occur over tens to hundreds of millions of years, depending on mass distribution and impact parameters. The system is a snapshot of a transient phase in disk evolution, caught between the initial collision and the eventual dispersal of the wave. The intruder itself may now be displaced, visible as a companion with its own disturbed structure. Its passage is a reminder that galaxies are not isolated islands, but members of environments where encounters are inevitable. Even a single close passage can reorganize gas, and gas is the ingredient that decides whether the encounter becomes merely a distortion or a luminous burst. The ring also shows how triggered star formation can be organized by pure dynamics. No bar is required, and no long-lived spiral pattern is required. A single impulsive event can restructure gas into a coherent, expanding pattern, and the resulting star formation can be both intense and spatially ordered. The cartwheel, therefore, connects back to Chapter 1, where collisions reshaped galaxies through tides and shocks. Some encounters merge and erase disks, building spheroids and tidal tails. Others punch through, leaving rings and wave patterns that persist long after the intruder moves on, like fingerprints of a momentary impact. Ring galaxies become laboratories because their geometry isolates cause and effect. The wave front is a controlled experiment in compression, collapse, and feedback. By comparing ages around the ring, we can test star formation recipes against a known dynamical trigger, and we can ask whether feedback limits the burst in the same way it does in compact nuclear starbursts. Feedback appears here too, because the ring's massive stars inject energy into the compressed gas. Supernovae and winds can carve bubbles, disrupt clouds, and limit efficiency. Even in a triggered ring, the burst must negotiate with its own products, and the ring can become patchy as some regions are quenched while others continue forming stars. The cartwheel also raises the question of what happens to the gas after the wave passes. Some gas is consumed into stars, some is heated and dispersed, and some may flow inward due to torques induced by the disturbance. The collision can therefore seed both ring star formation and later central activity, even if the central region looks quiet in the immediate snapshot. Across M82 and the cartwheel, the theme is consistent and unsettling. Starbursts are factories that can build stellar mass rapidly, but they can also expel the very material they need. The galaxy's future is shaped by whether gas is retained, recycled, or lost, and by whether the burst leaves behind a stable disk or a disturbed remnant. This is not only a local story, because starbursts were more common in the early universe. High gas fractions and frequent interactions made intense star formation routine. The metals and dust produced in those epochs helped set the conditions for later galaxy cooling and planet formation, and they helped transform pristine hydrogen and helium into the chemically rich cosmos we inhabit. When we look deep in time, we are also looking at different typical conditions. Young galaxies were more compact, more gas-rich, and more turbulent, and their star formation was often clumpier. In that context, what we call a starburst nearby may have been closer to normal at high redshift, which raises a quiet question. Are we defining rarity, or are we defining an extreme relative to today's calmer universe? In that sense, starbursts are part of the universe's autobiography, written in heavy elements and in the structure of halos. They connect stellar evolution to galaxy evolution, and they connect visible light to the hidden reservoirs of gas. They also remind us that brightness can be a brief phase rather than a stable state, and that what looks like a climax may be only an interlude. We end this chapter with a final inversion of the opening hook. The points of light in a starburst can be dazzling, but they still do not tell us where most mass resides. Even in these luminous factories, gravity is often dominated by something we cannot see, and the motions of gas and stars continue to hint at an unseen scaffold. The next mystery follows that absence, toward galaxies whose gravity is real, but whose starlight is almost missing. We move from feedback written in light to mass written in motion, and the journey turns toward the dark. We leave Chapter 4 with starburst factories blazing, converting gas into light with ruthless speed. Now we confront the opposite extreme, galaxies where star formation barely happened, and the missing light becomes the clue. The camera cools from incandescent nebulae to dim outskirts, where even long exposures struggle to gather photons. In this quieter regime, the universe seems almost reluctant to reveal itself, and that reluctance is the story. A galaxy can look faint because it is small, because it is distant, or because dust hides it behind a veil of extinction. Astronomers learn to separate those possibilities by combining color, size, and redshift, then testing each interpretation against physics. They also watch how surface brightness behaves, because distance dims extended objects in a distinctive way. This chapter focuses on a stranger case. The galaxy is faint because it never made many stars, yet its gravity still shapes motion. It is a paradox you can measure because the absence of light does not erase the pull of mass. The opening hook returns with sharper stakes. What if the points of light are not merely incomplete, but radically misleading about where mass lives? If most matter is dark, then galaxies are only the visible frosting on an invisible structure. The metaphor is tempting, but the reality is stricter. Gravity does not care about metaphors, and it does not negotiate. It leaves signatures in trajectories, in distortions, and in the way systems refuse to fly apart. When we follow those signatures carefully, the darkness stops being an idea and becomes a set of numbers. The problem is not philosophical, because gravity is measurable. We can map mass by watching how objects move and by watching how light bends. The tension shifts from spectacle to inference, and inference becomes the main instrument. On screen, the visuals change as well. Instead of bright H2 regions and blue clusters, we see graphs, spectra, and faint smudges whose importance is larger than their appearance. A cursor traces a line through noisy data points, and the line becomes a claim about the unseen. We begin with a primer that stays grounded in observables. In spiral galaxies, rotation curves measure orbital speed as a function of radius, turning a glowing disk into a dynamical experiment. Observers place a spectrograph slit across a disk, then read Doppler shifts as a velocity field. Gas and stars on one side move toward us, while the other side moves away, and the pattern sketches a wheel in motion. Radio observations of neutral hydrogen can extend this wheel far beyond the bright stellar disk into regions where starlight is almost absent. If mass followed light, speeds would fall with distance, yet many curves stay flat. That expectation comes from a simple idea that works in the solar system. When most mass sits near the center, orbital speed declines roughly like the square root of 1 over radius. In a luminous galaxy, starlight often drops steeply beyond the bright disk, so the visible mass seems to thin out. Flat rotation curves imply that enclosed mass keeps rising where starlight declines. The simplest reading is an extended halo of unseen matter. This is not a single galaxy's oddity, because the pattern repeats across many disks. Even when we correct for gas mass and for the faint outskirts of the stellar population, the discrepancy remains. Historically, the shock was not only the result, but the consistency. Early hints appeared in the 1970s when Vera Rubin and collaborators measured rotation in spiral galaxies with unprecedented reach. Their spectra revealed outer velocities that refused to drop, even as surface brightness faded into the background. The data did not fade the way the light did, and the mismatch was stubborn. It suggested that the luminous disk was riding inside something larger, something heavier, and something mostly invisible. That invisible component became a central character in modern cosmology, long before we could simulate it in detail. Earlier still, Fritz Zwicky had argued for missing mass in galaxy clusters, using their internal motions as evidence. The idea matured slowly, because it demanded a new kind of humility about what telescopes actually show. In galaxies without clean disks, we use a different tool. Stellar velocity dispersion measures how fast stars move in random directions, and it is especially useful for spheroidal systems. Instead of a tidy rotation pattern, the system behaves more like a swarm, with stars crossing and recrossing the center. Higher dispersion at a given size implies deeper gravity, even when the galaxy looks dim. Spectral absorption lines broaden when stars have a spread of velocities, and that broadening becomes a proxy for the depth of the potential well. The method leans on the virial theorem, a deceptively simple relationship linking kinetic energy to gravitational binding. In plain terms, fast motions require strong gravity, or else the system would dissolve. A third observable is gravitational lensing. Mass bends spacetime, and spacetime bends light paths from background sources. In the sky, the effect can look like a subtle shear, stretching distant galaxies into aligned ellipses. In stronger cases, it produces arcs, rings, and multiple images, as if the universe were a fun house mirror with perfect mathematical rules. Lensing can weigh galaxies and clusters even when the mass is not luminous. It is especially powerful because it does not require the system to be in equilibrium, only that light passes by the mass. In a wide field map, thousands of tiny distortions add up into a statistical portrait of where matter sits. These three methods do not always agree in detail, and that disagreement is part of the science. Each method samples different scales and assumptions, and each has systematic uncertainties. Rotation curves depend on inclination and non-circular motions, while dispersion requires assumptions about orbital anisotropy. Lensing depends on geometry and line-of-sight structure, where unrelated mass can add confusion. Yet together they point to the same conclusion. Light alone cannot explain the gravity. The convergence is the key, because it is hard to fool three different techniques in the same direction. At this point, the narration pauses for a careful distinction. The evidence is not that we are missing a few stars or undercounting faint ones at the edge. The evidence is that the gravitational field behaves as though additional mass exists, distributed differently than the visible matter. That difference is what makes the problem so productive. It forces us to ask not only how galaxies shine, but how they are held together. It also forces us to treat darkness as structure, not as emptiness. The modern framework that absorbs this evidence is lambda CDM. Lambda represents dark energy driving accelerated expansion, and CDM represents cold, dark matter that clumps and seeds structure. In this picture, galaxies form inside dark matter halos that assemble hierarchically, merging and accreting over cosmic time. The model is not a single equation, but a set of linked assumptions that can be tested in simulations and surveys. It predicts a universe where the invisible mass collapses first, then invites ordinary matter to follow. The success is not aesthetic. It is practical, because it reproduces the large-scale web seen in galaxy surveys and in the cosmic microwave background. Cold matters because it moves slowly enough to clump early. If the dark component were too fast, it would stream out of small density peaks and erase structure on small scales. Dark matters because it does not emit or absorb light in ordinary ways. It does not radiate away energy, so it cannot collapse into a thin disk like gas. The halo forms the gravitational scaffold, and baryonic gas falls in, cools, and sometimes forms stars. That word "sometimes" is doing heavy work because it hides a complicated chain of conditions. It also hides the fact that baryons can fight back, pushing on the scaffold through feedback and outflows. Cooling is not automatic, and star formation is not guaranteed. Gas must shed energy through radiation, often via atomic lines and, in colder phases, molecular transitions. It must reach sufficient density to become gravitationally unstable, then fragment into clouds that can collapse. Magnetic fields, turbulence, and feedback can slow or redirect that collapse, and the details matter. Many halos should exist that never become bright galaxies, because baryons can be heated, expelled, or prevented from cooling. The missing light is therefore not a single mystery, but a family of outcomes. In some cases, the gas arrives but stays warm. In others, it arrives briefly and is thrown out again, leaving only a faint stellar trace. We enter that family through ultra-diffuse galaxies, or UDGs. A UDG has very low surface brightness, meaning its starlight is spread thin across the sky. In practice, surface brightness sets the difficulty of detection because the galaxy competes with the glow of the night sky and the scattered light of nearby stars. It also has a large effective radius, meaning it is physically extended for its luminosity. The result is a ghostly presence, large enough to notice once you know where to look, yet faint enough to vanish in shallow images. On screen, the galaxy emerges only after careful background subtraction, as if the data itself must be persuaded to confess. UDGs look like galaxies that have been inflated without being filled. They can have sizes comparable to normal disks, yet contain far fewer stars. Visually, they resemble pale watercolor washes, with no bright knots of star formation and no sharp central bulge. Their colors are often muted, hinting at older stellar populations and little recent activity. Their existence forces a question about formation. Are they failed giants or expanded dwarfs or both? The answer matters because it tells us how tightly starlight tracks halo mass and where that relationship breaks. If the mapping is loose, then luminosity becomes a poor guide to the underlying cosmic inventory. Several pathways are plausible, and the debate is active. Feedback from supernovae can puff up stellar distributions by repeatedly stirring gas and changing the central potential. When gas is driven out and later falls back, the gravitational field fluctuates, and stellar orbits can migrate outward. Over many cycles, the inner density can be lowered, and the galaxy can become more extended. Tidal heating can expand a galaxy as it orbits in a group or cluster, stretching and loosening it. The process is slow and cumulative, like bending a paperclip back and forth until its shape changes. In a cluster, even the background gravitational field is time-dependent because encounters are frequent and relative speeds are high. Another pathway invokes high-spin halos. If a halo has unusually high angular momentum, gas can settle into a larger, lower-density disk. Star formation then proceeds inefficiently because the gas never reaches the densities that collapse easily. In plain terms, the material is spread too thin to ignite sustained starbirth. The idea links a visible property, diffuseness, to a hidden one, the halo's spin, which is set by cosmic torques during assembly. Those torques arise from the surrounding matter distribution, so even a ghost galaxy carries an imprint of its larger-scale environment. These explanations are not mutually exclusive. Nature can produce similar-looking ghosts through different histories, especially when environment adds its own pressure. The challenge is to connect each faint smear of light to a specific dynamical story. That connection requires more than a pretty image. It requires kinematics, stellar populations, and a sense of context within the surrounding cosmic neighborhood. It also requires patience, because low-surface brightness astronomy punishes haste with false detections and biased measurements. Dragonfly 44 becomes our first case study because it sharpened the argument. It is an ultra-diffuse galaxy discovered in deep imaging designed to detect low-surface brightness structures. The Dragonfly telephoto array, built from multiple camera lenses, was optimized to suppress scattered light, which often drowns out faint extended objects. That design choice is a reminder that discovery is sometimes an engineering problem. Dragonfly 44 sits in the Coma cluster environment, where tides and interactions are common. Coma itself is a dense metropolis of galaxies wrapped in hot X-ray-emitting gas and threaded by dark matter. At first glance, Dragonfly 44 looks like a large galaxy that forgot to turn on. Its starlight is faint and smooth, and it lacks the dense central brightness typical of massive systems. In a wide shot of Coma, it is easy to miss, because brighter galaxies pull the eye away. A slow zoom reveals it as a diffuse oval, barely brighter than the background sky. Yet the key question is not how it looks, but how strongly it holds itself together. A galaxy's appearance can lie, but its dynamics must add up. Astronomers infer its mass through stellar velocity dispersion. They measure the line-of-sight speeds of its stars, then model the gravitational potential needed to keep those stars bound. The method is conceptually simple, but technically demanding, because the signal is faint and the stars are distant. Each spectrum is noisy, and each absorption line must be extracted with care. Templates of known stellar spectra are matched to the data, and the best fit broadening becomes the velocity spread. A high dispersion in a faint galaxy implies a heavy halo. It means the stars are moving too fast to be held by their own visible mass alone. Another clue comes from globular clusters. Massive halos tend to host more globular clusters, and counts can correlate with halo mass. Globulars are compact and bright enough to be counted even when the galaxy's diffuse light is hard to measure. They act like luminous tracer particles, orbiting in the halo and preserving information about its depth. Dragonfly 44 appears to host an unusually rich globular cluster system for its starlight. That richness is a second line of evidence, pointing toward an unexpectedly massive dark component. It also hints at an early epoch of star formation, because globular clusters tend to form when gas densities and pressures are high. The combined inference is startling. Dragonfly 44 may sit in a halo comparable to the Milky Way's, yet it contains only a tiny fraction of the Milky Way's stars. It is not simply dim, it is inefficient. The word inefficient here is not an insult, but a quantitative diagnosis, because it compares the expected baryon content to the observed stellar mass. If the cosmic baryon fraction sets a baseline, then Dragonfly 44 looks like a system that never cashed in its available fuel. The question becomes unavoidable. Where did the baryons go, and when did they fail to settle? Star formation inefficiency becomes the next bridge in the narrative. If a halo is massive, why did it not convert gas into stars? The answer is not one mechanism, but a sequence of barriers that can operate at different times. Some barriers act early, before the first long-lived stars can accumulate. Others act later, after a galaxy has already formed a fragile stellar body. The timing matters, because it determines whether a system ends as a puffed-up remnant or a barely started seed. It also determines what evidence remains, because old stars remember early conditions in their chemistry. Ionization is the first barrier for small halos. When the first stars and galaxies ionized the intergalactic medium, the gas was heated. Hydrogen that was once neutral became ionized, and that ionization raised the temperature of the diffuse cosmic gas to around 10,000 Kelvin. Hotter gas resists falling into shallow potentials, and existing gas can be evaporated or prevented from cooling. In effect, the universe turned on a background heater, and the smallest wells could no longer hold on to their fuel. The ionization era was not instantaneous, and it was not uniform. Patches of the cosmos lit up at different times, so a halo's location could decide its fate. Supernova feedback is another barrier, especially in low-mass systems. Explosions inject energy and momentum, driving winds that can expel gas. A single supernova can release about 10 to the 51 ergs of energy, and clustered supernovae can act like a sustained engine. Repeated bursts can keep gas cycling without settling into long-lived dense clouds. The result is a galaxy that breathes, gas out, gas in, without ever building a stable reservoir for star formation. The breathing can also reshape the dark matter distribution indirectly, because changing the central mass profile changes the gravitational potential. Environmental stripping adds a third barrier, especially in clusters like Coma. Ram pressure from hot intracluster gas can strip a galaxy's cold gas as it moves through the medium. The force depends on the density of the intracluster plasma and the square of the galaxy's velocity, so fast orbits can be punishing. Tidal forces can remove outer material and heat the remaining stars. In a cluster, galaxies are not isolated laboratories. They are objects in traffic, buffeted by a medium that is itself a product of deep gravitational wells. Even the faintest galaxies feel the collective weight of the cluster's dark halo. These processes can cooperate. Ionization reduces the initial gas supply, feedback removes what remains, and the environment prevents replenishment. Even if some gas survives, it may be kept warm or turbulent, unable to settle into the cold molecular phase that forms stars efficiently. The end state is a galaxy that is large in size, small in light, and heavy in dark matter. That combination is exactly what makes UDGs such incisive tests of theory. They are not merely curiosities, they are boundary conditions for how galaxies can fail. Dragonfly 44 therefore tests lambda CDM in a specific way. It probes how baryons populate halos and how scatter and star formation efficiency arises. It also tests whether UDGs are a single class or a mixed population. If some UDGs live in massive halos, they may represent quenched or failed large galaxies. If others live in modest halos, they may be dwarfs stretched by feedback and tides. The same silhouette on the sky could hide very different origins. That ambiguity is not a weakness. It is an invitation to gather the missing measurements. The story then pivots to the other extreme, where the galaxy is not large and diffuse, but tiny and nearly starless. Segway 1 is an ultra-faint dwarf spheroidal satellite of the Milky Way. It contains so few stars that it was only recognized with modern surveys. In images, it is barely a pattern at all, more like a statistical overdensity than a classic object. The camera lingers on a sparse star field, then overlays a subtle contour map that reveals a faint concentration. Yet that near invisibility is exactly why it matters. Ultra-faint dwarfs are defined by extremely low luminosity and old, metal-poor stellar populations. Their stars tend to be ancient, formed when the universe had produced only small amounts of heavy elements. They are not forming stars now, and many likely stopped early. Their color magnitude diagrams show thin, old sequences, like a population that aged without replacement. They are important because they may preserve conditions from the early universe. In a sense, they are fossils, not because they are dead, but because they are minimally altered. They offer a glimpse of what galaxy formation looks like when it barely gets started. Segway 1 is also a methodological challenge. With so few stars, membership becomes the central problem. Astronomers must decide which stars belong to the dwarf and which are foreground Milky Way stars. A single misidentified star can skew the inferred velocity dispersion, and that dispersion is the key to the mass estimate. The analysis, therefore, becomes careful and conservative, with explicit error budgets that reflect the small sample. Observers often return for repeat measurements, because one epoch can be fooled by a binary star's orbital motion. Membership is established through velocities and chemical fingerprints. Stars in the same dwarf share a narrow range of positions on the sky, similar line-of-sight velocities, and often similar low metallicities. Metallicities are measured through spectral line strengths, which encode the abundance of elements heavier than helium. In ultra-faint dwarfs, those abundances can be extremely low, reflecting limited chemical enrichment. Spectroscopy turns each star into a data point in a gravitational experiment. Each point is precious because the system offers so few. When the data are plotted, the member stars cluster in velocity space like a small island in a noisy sea. Even a small sample can be powerful if the signal is clear. If the star's velocity dispersion is higher than their visible mass can support, then unseen mass is required. In Segue 1, the inferred dispersion implies a deep potential well for such a tiny light output. The stars move as though they are embedded in something far more massive than themselves. The invisible component does not sparkle, yet it dictates the choreography. The effect is almost unsettling because it makes the stars feel like test particles in a much larger gravitational field. This leads to the concept of mass-to-light ratio. In intuitive terms, it compares how much gravity a system has to how much starlight it emits. Astronomers often express it in solar units, comparing the system's mass and luminosity to the sun's. A high mass-to-light ratio means the system is mostly mass with very little light. It is one of the cleanest ways to quantify the phrase dark matter dominated. It also reminds us that light is a biased tracer because it comes from a small fraction of the total matter budget. Segue 1's mass-to-light ratio is among the highest known. It is often described as one of the most dark matter-dominated galaxies discovered. That description is not poetic. It is a quantitative statement about gravity exceeding the contribution of stars. When the ratio climbs into the hundreds or thousands, the stars become mere tracers, like a few glowing embers floating in a much larger invisible furnace. The furnace metaphor is imperfect. Dark matter does not radiate heat, but the scale mismatch is real and measurable. Such systems become prime targets for indirect dark matter searches. If dark matter particles can annihilate or decay into photons or other particles, dense dark matter concentrations could produce detectable signals. Gamma-ray telescopes and other detectors can search for excess emission from the direction of dwarf spheroidals. Dwarf spheroidals are attractive because they have high inferred dark matter density and low astrophysical backgrounds. They lack the messy star formation and gas dynamics that complicate the centers of larger galaxies. In the best case, a faint excess would connect galactic dynamics to particle physics, linking rotation curves to a microscopic process. Yet the uncertainties must be stated clearly. The dark matter distribution depends on dynamical modeling, and small number statistics can inflate errors. Foreground contamination, binary stars, and non-equilibrium effects can bias dispersion measurements. Binary motion can mimic extra velocity dispersion if not accounted for, especially when only a few stars are observed. Tidal effects from the Milky Way can also disturb a dwarf, complicating the assumption of equilibrium. The science advances by confronting these caveats directly, not by ignoring them. Each caveat becomes a reason to improve the data, not a reason to abandon the question. Even so, the broader implication remains. If ultra-faint dwarfs are real dark matter reservoirs, They constrain particle properties and structure formation. They also test whether lambda CDM predicts the right number and internal structure of small halos. In simulations, the smallest halos form early, and many should survive as substructure. Observationally, the faintest dwarfs are hard to find, so each new discovery reshapes the census. Surveys must correct for sky coverage and detection limits, because what we see is only a slice of what exists. This is where the chapter reconnects to cosmic structure. In hierarchical formation, small halos form first and merge into larger systems. Dwarf galaxies are therefore not side characters. They are the building blocks that assembled the big galaxies we see. When we map the motions of a tiny system like Segway 1, we are probing the lower limit of galaxy formation, where the rules may change. We are also probing the earliest surviving architecture of the Milky Way's own assembly history. But the observed dwarf population raises tensions. The missing satellites problem notes that simulations predict more small subhalos around galaxies like the Milky Way than the number of observed satellites. Some of that gap is observational because the faintest objects hide against the stellar foreground and require wide, deep surveys. Some of it may be physical because many halos may never form stars at all. The too big to fail problem notes that the most massive predicted subhalos seem too dense to host the faint dwarfs we observe. The phrase points to a mismatch between simulated inner densities and the measured kinematics of real satellites. The tension is sharpened by the fact that the brightest dwarfs are not obviously living in the densest predicted subhalos. These tensions do not automatically overturn lambda CDM. Baryonic physics can alter subhalo structure, and observational incompleteness can hide faint satellites. Supernova-driven outflows can reduce central densities, and tides can reshape satellites over time. Survey selection effects can bias what we detect, especially near the galactic plane. Yet the tensions keep the field honest. They force better simulations, better surveys, and sharper comparisons. They also encourage a disciplined question. Are we missing galaxies or misunderstanding how galaxies occupy halos? Dragonfly 44 and Segway 1 bracket the chapter's theme. One is extended and diffuse, possibly sitting in a massive halo with few stars. The other is tiny and ultra-faint, yet its stars move as if held by a heavy, invisible hand. They are different silhouettes of the same underlying idea. Light is optional, but gravity is not. If you want to find the mass, you follow what moves, and you follow what bends. Together, they clarify what it means to map the invisible. We do not see dark matter directly, but we see its gravitational bookkeeping in motions and lensing. We infer the scaffold by the way luminous matter is forced to behave. In a rotation curve, the outer gas refuses to slow down. In a dwarf spheroidal, stars move too fast for the light they carry. In lensing maps, background galaxies align as if pulled by a mass they cannot see. The universe leaves receipts, even when it hides the purchase. This inference loops back to earlier chapters in a new way. In Chapter 3 and Chapter 4, engines of feedback shaped gas and starlight, sometimes quenching and sometimes igniting. In these ghost galaxies, the engines may have been starved from the start, or shut down early by heating and stripping. The same physical processes appear again, but with different outcomes because the initial conditions differ. A shallow potential amplifies the effect of heating, while a dense environment amplifies the effect of stripping. The contrast is instructive because it shows how the same physics can create either fireworks or silence. The central question tightens again. How do galaxies form and transform when the dominant component is unseen? If dark matter sets the potential, then baryons are responding actors, not the stage itself. That perspective changes how we interpret a faint galaxy. Instead of asking only what it lacks, we ask what its halo allowed and what its environment demanded. We also ask what timing permitted, because a halo that forms early meets a different radiation background than one that assembles late. The chapter also reframes what counts as a galaxy. If a system has only a few hundred or thousand stars, is it still a galaxy or a star cluster? The distinction often rests on dark matter. A galaxy is a stellar system embedded in a dark halo, while a cluster is mostly stars bound by their own gravity. In practice, the boundary can be fuzzy, because both can be small and both can be old. The ambiguity is not semantic. It determines whether we treat an object as a tracer of cosmology or as a product of stellar dynamics alone. Segue 1 sits near that boundary, which makes it scientifically valuable. If it is truly dark matter dominated, it is a minimal galaxy. It is a test case for how small a galaxy can be while still being a galaxy. It also raises a deeper question: how many similar systems exist, unseen, because they contain too few stars to announce themselves? If halos can be almost starless, then the Milky Way may be surrounded by a population of dark companions that are detectable only through their gravitational effects. What would it mean to live in a galaxy whose neighborhood is crowded with invisible neighbors? Dragonfly 44 challenges the opposite boundary. If it truly has a massive halo, it is a maximal failure of star formation. It suggests that halo mass alone does not guarantee a bright galaxy, and that the baryonic conversion factor can vary wildly. The implication is uncomfortable because it means the mapping from halo to galaxy is not one-to-one. It is probabilistic, shaped by timing, feedback, and environment. The ghosts are telling us that the universe can build a deep gravitational well and still leave it dim. The story then widens to the cosmic web. Dark matter halos merge, accrete, and form filaments that guide gas flows. In simulations, those filaments look like luminous threads when rendered by density, connecting nodes where clusters form. Galaxies light up where gas can cool inside these wells, and they fade where gas cannot remain cold. The web is not merely a backdrop. It is a delivery system for matter, and it sets the routes along which galaxies grow. If the camera pulls back far enough, individual galaxies become sparks on a vast, faint lattice. In that sense, dark matter is the universe's first draft. It writes the large-scale structure before most stars exist. Then baryons revise the draft with light, metals, and feedback. The autobiography metaphor becomes literal. Gravity writes the outline, and starlight fills in selected paragraphs. The blank spaces are not empty. They are places where the outline exists without the illumination. The question that lingers is simple to ask and hard to answer. How much of the cosmic story is written in those blank spaces? We also acknowledge what we do not yet know. We do not know the particle nature of dark matter, or whether it is one species or many. We do not know whether small-scale tensions point to new physics or to complex baryonic effects we are still learning to model. The honest position is not uncertainty for its own sake. It is uncertainty with boundaries, constrained by what motions and lensing already demand. Whatever dark matter is, it behaves gravitationally like a cold, collisionless component on large scales. But the observational program is clear. Measure motions in faint systems, count satellites with deeper surveys, and map lensing across cosmic time. Each method is a different way of reading the same invisible text. As instruments improve, the ghosts become less metaphorical and more catalogued, with velocities, sizes, and stellar histories attached. The act of detection becomes part of the narrative because the universe hides these objects in plain sight. Every improvement in background, subtraction, and calibration is, in a quiet way, an improvement in cosmology. The chapter ends by turning forward in time and backward in distance. Dark matter shapes the scaffold, but the earliest galaxies show the first lights on that scaffold. To see them, we must look deeper into the past, where detection itself becomes the challenge. The faintness is no longer only about missing stars in nearby halos. It becomes about the first stars and galaxies, whose light has been stretched and dimmed by expansion. Even the brightest beginnings become fragile signals after billions of years of travel. We move into Chapter 6 with a new kind of suspense. The question is no longer what powers the brightest galaxies. The question is how the first galaxies emerged from darkness, and how we can detect their faint beginnings at the edge of time. We leave Chapter 5 with gravity mapped in shadows, where mass outweighs light. Now the journey flips toward barely visible photons, where distance becomes time. Dark matter gave us a scaffold we could infer without seeing it, traced by its pull on galaxies and gas. The early universe offers the opposite challenge. Light exists, but it arrives stretched, dimmed, and easily misread. To travel outward now is to travel backward, and that reversal is not poetic license. The farther we look, the younger the cosmos becomes, because light needs time to cross expanding space. This is the edge of time rule that makes astronomy a time machine, even when the images look still. We do not see galaxies as they are now, but as they were when their photons left. As the camera drifts across a deep field, the scene looks calm. Black velvet, scattered pinpricks, a few pale smudges. Yet every faint patch is a timestamp, and some of those timestamps predate the Milky Way itself. We pause on a simple but unsettling fact that reshapes everything we measure. The universe expands while the light is in flight, and that expansion changes the light itself. Cosmological redshift is not a Doppler trick from motion through space, like a siren changing pitch. It is the stretching of space, which stretches every wavelength carried within it. In everyday terms, the photon is not losing speed, and it is not being slowed down by a medium. Instead, the ruler used to measure its wavelength is being pulled longer, and the light is forced to match. Early galaxies emitted much of their power in ultraviolet and visible light, where hot young stars blaze. By the time that light reaches us, the wavelengths have been pulled into infrared. That shift is not a small correction at the edge of time, but a wholesale relocation of the signal. A galaxy that once glowed blue-white can arrive as a faint ember, visible only to cold infrared eyes. Redshift becomes the conversion factor between then and now, and it is written directly into the spectrum. A higher redshift means a smaller scale factor at emission and a younger cosmic age. We define it carefully because the numbers carry the story, and the story is easy to misread. The scale factor A relates to redshift by 1 plus z equals 1 over A. That relation is more than notation, and it is more than a convenient label for distance. It tells us the universe was denser, hotter, and faster evolving when those photons began their journey. In the background, the cosmic microwave background offers a reference point, an afterglow from when the universe was about 380,000 years old. Everything we are chasing here happens long after that glow formed, yet still astonishingly early. Look back time is the clock we read from the sky, and it is a clock with a particular kind of honesty. It is not the age of the galaxy today, but the time the light has been traveling. If a galaxy is observed at a look-back time of 13 billion years, we are not seeing an ancient relic in the present. We are seeing a young system in its own era, caught mid-formation. Comoving distance is the map coordinate we use to compare structures across expansion, so we do not confuse growth with geometry. Proper distance changes with time, and that distinction prevents false intuition. Even the word distance becomes slippery here, because the universe does not offer a single frozen measuring tape. In an expanding universe, distance is tied to the model of expansion, not a single ruler. So we carry forward the central question in a new form, sharpened by the fact that our evidence is delayed. How do galaxies form and transform when we can only see their earliest chapters? The observational tension is immediate, and it is not solved by simply building larger mirrors. The first galaxies are not only far, they are faint in a way that punishes every detector. Surface brightness dims rapidly with redshift, and it dims faster than most people expect. Expansion spreads photons over larger apparent areas and stretches their arrival times, making extended objects fade. This is the Tolman surface brightness effect in practice, and it scales steeply with redshift. Even if a galaxy's total luminosity is high, its light can be diluted into invisibility across the detector's pixels. Cosmic dimming stacks with intrinsic smallness, and the early universe does not hand us giant spirals. Early galaxies are compact and low mass, so their total light budget can be modest even when active. On screen, the faintest candidates look like soft grains of light, barely distinct from the background. The eye wants to call them noise, and sometimes that instinct is correct. The sky adds its own obstacles, and they are not dramatic, but they are relentless. Zodiacal light, thermal backgrounds, and detector noise compete with signals that may be only a few photons. Zodiacal light is sunlight scattered by dust in our own solar system, a subtle glow that never fully disappears. Thermal emission comes from warm surfaces, which is why infrared telescopes must be cooled and shielded. Contamination is the quiet enemy of deep surveys, because the universe is full of lookalikes. A nearby dusty galaxy can mimic a distant one, and a cool star can mimic a red-shifted spectrum. Even cosmic rays and detector artifacts can masquerade as sources when exposures are long and the signal is weak. The deeper we go, the more the survey becomes a test of discipline, not just sensitivity. So we explain how candidates are found, and why the method is both powerful and vulnerable. Wide imaging surveys search for objects that disappear in bluer filters and reappear in redder ones. This dropout pattern is the Lyman break in action, and it is rooted in atomic physics. Neutral hydrogen absorbs photons shortward of Lyman alpha, creating a sharp spectral cliff. More precisely, Hydrogen's electronic transitions carve away the ultraviolet continuum, and the intergalactic medium adds a forest of absorption lines. The result is a dramatic drop that can be recognized even with broad filters. At high redshift, that cliff slides into infrared bands, carried there by the expansion itself. The galaxy looks absent in optical images, then suddenly present in near infrared. Visually, the survey becomes a flipbook of filters, where a source blinks into existence only at longer wavelengths. That blink is not a trick of the instrument, but a signature of the universe's history. Photometric redshift turns this color behavior into a probability, rather than a single claim. It fits templates to broadband fluxes and returns a likely Z with uncertainties. Those templates encode assumptions about stellar populations, dust attenuation, and emission lines, and each assumption can tilt the answer. Photometry is efficient, but it is not final. Dust reddening, old stellar populations, and strong emission lines can imitate the same colors, especially when the signal-to-noise is low. In the worst cases, a nearby object can wear the costume of the early cosmos. Spectroscopic confirmation is the hard currency because it anchors the story to specific physics. It measures specific lines or breaks at known rest wavelengths, locking the redshift to a physical reference. We explain why lines matter and why observers become cautious when only one line appears. A single emission line can be misidentified, so observers seek multiple features or consistent line ratios. A line's observed wavelength is only half the clue, because several different transitions can land in the same band. The spectrum must tell a coherent story. Continuum shape, break position, and line pattern must agree. In the early universe, the key feature is often Lyman alpha, but it is complicated and sometimes absent. The intergalactic medium can absorb it during reionization, erasing what would otherwise be a bright beacon. Lyman alpha is also resonant, meaning it scatters easily, and that scattering makes it sensitive to gas motions and geometry. A small change in neutral hydrogen can turn a strong line into a whisper. Other lines become crucial when Lyman alpha is suppressed, and they carry their own diagnostics. Oxygen and hydrogen recombination lines can appear, shifted into infrared, where new instruments excel. These lines are more than redshift markers because they probe temperature, density, and ionization state. They hint at whether the gas is pristine or already enriched by earlier stars. This is where the chapter's climax engine enters, not as a symbol, but as a tool built for a specific problem. The James Webb Space Telescope is built for stretched light, and it changes what counts as observable. JWST is not just bigger than Hubble, although its mirror does gather more photons. It is colder, infrared optimized, and designed to work where the earliest galaxies now shine. A vast sun shield blocks heat and sunlight, allowing the telescope to settle into a stable thermal environment. In infrared astronomy, temperature is not comfort. It is noise control. NIRCam provides deep imaging in multiple infrared bands, and it is designed for both discovery and morphology. It finds candidates by their breaks and colors, then maps their shapes and clustering. Those shapes matter because even a tiny blur can hint at structure, size, and multiplicity. In some fields, what looks like one source resolves into two, suggesting an early merger in progress. NEIR spec provides spectroscopy with sensitivity and multiplexing, which changes the pace of confirmation. It can confirm redshifts and measure lines that reveal physical conditions. Multiplexing means many targets can be observed at once, turning a handful of heroic detections into a population study. The frontier becomes less anecdotal and more statistical. Together, they turn faint smudges into data-rich systems, and they turn wonder into constraints. They convert a detection into a measurement, and a measurement into a test of theory. We connect this to the earlier chapter's engines because the same physics is present in a younger costume. Feedback and starbursts shaped galaxies later, but here we ask how fast the first engines ignited. We also connect to the dark scaffold from Chapter 5, because baryons do not choose their stage. These early lights are baryons responding to halos that formed even earlier in the dark. In simulations, the first halos assemble from tiny density fluctuations imprinted in the early universe. Gravity amplifies those fluctuations, and the dark matter collapses first, providing potential wells for gas. Gas falls in, shocks, cools, and fragments, but only if it can shed energy efficiently. At the beginning, with few heavy elements, cooling relies on hydrogen and helium, and sometimes on molecular hydrogen. Now we step into a specific milestone that predates JWST, and we treat it as a boundary stone. GNZ11 became a symbol of how far the Hubble era could reach. GNZ11 sits at very high redshift, seen when the universe was only a few 100 million years old. It pushed the frontier before Webb arrived. Its discovery relied on deep imaging and dropout selection, refined through years of deep field practice. It appeared in infrared bands while vanishing in optical, consistent with a strong Lyman break. The Hubble Ultra Deep Field and its successors trained astronomers to trust patterns across filters, but also to distrust easy conclusions. Each candidate demanded careful checks because the stakes were high. Follow-up work aimed to secure the redshift and rule out imposters, using every line of evidence available. The debate itself showed how fragile early universe claims can be. That fragility is not a weakness of science, but a feature of its standards. Extraordinary distance requires extraordinary scrutiny, because a small mistake can move a galaxy billions of years in time. GNZ11 mattered because it was unexpectedly bright for its epoch, and brightness is never just brightness. Brightness at that time implies rapid star formation or unusually efficient light production. We unpack what brightness can mean physically, because several levers can be pulled at once. It can reflect high star formation rates, low dust extinction, or a top-heavy stellar population. A top-heavy population means more massive stars than we see in typical nearby regions. And massive stars are ultraviolet factories. They live fast, die young, and flood their surroundings with ionizing radiation. Brightness can also reflect geometry and timing because star formation is bursty. We may be catching GNZ11 during a brief flare-up when many hot stars are present at once. It can also reflect selection bias, which is a quiet but powerful sculptor of early samples. The brightest objects are easiest to find, so early samples can overrepresent rare luminous systems. Even with that caution, the implication is sharp because the universe does not wait for our expectations. Some galaxies were assembling stars quickly, only a few 100 million years after the beginning. That pushes us into the Ryanization context, where the first lights do more than decorate the sky. The early universe began neutral, then became ionized again as the first sources turned on. We define the cosmic dark ages, and we define them carefully, because dark here means starless, not empty. After recombination, the universe cooled and neutral hydrogen filled space with no stars yet to light it. Matter was present everywhere, but it was diffuse and it was chemically simple. The dominant atoms were hydrogen and helium, and the temperature was falling as the universe expanded. Then the first stars formed in small halos, where gas could finally collapse to high densities. Their ultraviolet photons began carving ionized bubbles in the surrounding neutral hydrogen. On a visualization, reionization looks like frost melting on a window, with clear patches spreading through a cloudy background. Each bubble is a region where hydrogen has been stripped of its electron. Reionization is the overlap of those bubbles, and overlap is the crucial word. As more galaxies formed, ionized regions grew and merged until most intergalactic hydrogen was ionized. This process matters because it changes what we can see, and it changes how light travels. Neutral hydrogen absorbs ultraviolet light, shaping the spectra of early galaxies. It also matters because it is a global phase change, not a local event in one galaxy. It marks when the universe became transparent to certain wavelengths again. We ask the key causal question because it links tiny galaxies to the largest possible scale. Did early galaxies produce enough ionizing photons to reionize the universe on the observed timeline? The answer depends on escape fraction and demographics, and both are difficult to measure directly. Ionizing photons must escape galaxies, and there must be enough faint galaxies to dominate the budget. Escape fraction is a simple phrase for a complex reality because gas is clumpy and dust is uneven. Photons can be trapped in dense regions, yet leak through channels opened by winds and supernovae. We infer the timeline through multiple probes, each one indirect but powerful. Quasar absorption spectra show the state of hydrogen, and the cosmic microwave background encodes integrated optical depth. Quasars act like flashlights shining through intergalactic gas, revealing absorption patterns that change with neutral fraction. The CMB, by contrast, records how many electrons the microwave photons scattered from over cosmic history. Galaxy surveys add a third constraint, and they do it by counting light. They measure the ultraviolet luminosity function, then extrapolate to faint populations we cannot yet detect. That extrapolation is where uncertainty hides, because the faint end is hard and the universe is large. If many small galaxies exist below detection, they could supply the missing photons. But the same physics that makes small galaxies common can also make them leaky, and that leakiness may be episodic. Feedback can open channels, increasing escape fraction in bursts. So the early universe becomes a coupling problem again, echoing themes we have already met. We must know how radiation and winds interact with clumpy gas at low metallicity. Low metallicity means fewer heavy elements, fewer efficient coolants, and different dust properties, which changes the structure of the interstellar medium. In plain language, the gas behaves differently when it is chemically young. We return to GNZ11 with this context, and we let it sit inside a larger landscape. If it is bright and young, it may represent a rare peak in the halo distribution. Rare peaks form early and grow fast because they begin with an advantage in the initial density field. They can host intense star formation, and they can bias our first impressions of typical early galaxies. Yet even rare peaks teach us, because extremes reveal the boundaries of possibility. They show what is physically possible when gas is abundant and cooling is efficient in primitive conditions. Historically, each new telescope has shifted the boundary between speculation and measurement, and the pattern repeats. Hubble made deep fields iconic, but it also revealed how quickly the frontier recedes when technology advances. Now the narrative accelerates into the JWST era, and the acceleration is measurable in confirmed redshifts. Webb does not merely extend Hubble, it changes the statistics and the certainty. Deep field programs search systematically, and they do it with procedures designed to resist self-deception. They combine long exposures, careful calibration, and repeated checks against contamination. Teams inject artificial sources to test recovery rates, they model completeness, and they compare independent reductions of the same data. The goal is not just discovery, but reliability. JD's is one of those programs, and its design reflects lessons learned from earlier surveys. It is designed to find and confirm galaxies at extreme redshift with both imaging and spectroscopy. From this effort emerges a landmark, and the landmark is not only a distance record. JD's GS Z14-0 becomes a new edge marker among the most distant confirmed galaxies. We introduce it as a test of the entire method, because method is what stands between us and illusion. A claim at such redshift must survive every alternative explanation and every instrumental caveat. Its photometry shows a strong break consistent with the Lyman limit, shifted deep into infrared, and the dropout is dramatic. The colors match an object from the earliest epochs. The source appears where it should, and it vanishes where it must, given the absorption of neutral hydrogen. That pattern is the first rung of the ladder, and it is persuasive, but not decisive. Then spectroscopy tightens the claim, and it does so by turning color into structure. Spectral features align with the expected redshift, reducing ambiguity that photometry alone cannot eliminate. We emphasize what confirmation means here, because it is easy to treat it as a stamp. It is not a single number, but a chain of evidence that rules out nearer dusty galaxies. The spectrum can show a sharp continuum, drop and specific emission features, and each feature carries a known rest frame identity. Each feature ties observed wavelengths to known physics. At such early times, even the presence of emission lines is informative, because lines require conditions. Lines imply hot stars, ionized gas, and rapid enrichment pathways. Ionized gas means ultraviolet photons are abundant, and abundance implies massive stars or accreting black holes. Rapid enrichment means earlier generations of stars have already lived and died, seeding the gas with metals. JADE's GS Z14-0 also carries a deeper surprise, and the surprise is not a single measurement. It appears more developed than naive expectations for such a young universe. We explain what developed means in measurable terms, because developed can sound subjective. It can mean higher stellar mass, stronger lines, or colors implying older stars already present. It can also hint at dust and metals earlier than expected, and that hint has consequences. Dust requires heavy elements, and heavy elements require earlier generations of stars. So we confront the existential tension, and we do it without rushing to a verdict. Are we truly seeing infancy, or are we seeing a universe that grew up faster than our models predict? The physical interpretation becomes the chapter's core argument, and it begins with thresholds. Early star formation must begin quickly once halos cross cooling thresholds. Those thresholds depend on mass and temperature because gas must radiate away energy to collapse. In the smallest halos, molecular hydrogen can help cooling, but it is fragile under ultraviolet radiation. Cold gas accretion along filaments can feed growth efficiently, and it can do so without dramatic shocks in certain regimes. In simulations, streams deliver fuel without shock heating in certain mass ranges. Visually, the cosmic web looks like luminous threads in a dark volume, converging on knots where galaxies form. Along those threads, gas flows like a river, invisible until it turns into stars. Mergers add another channel, and the early universe supplies them frequently. Small systems collide often at high redshift, building mass and triggering bursts in dense gas. A merger is not always a spectacular crash because early galaxies are small and gas-rich. Sometimes it is a quiet rearrangement that compresses gas just enough to ignite a new wave of star formation. Feedback complicates both channels because energy does not politely stay where it is produced. Supernovae can expel gas from shallow potentials, yet high inflow rates can replenish it rapidly. Radiation pressure and stellar winds can also stir the gas, changing its density structure and its ability to form stars. The same young stars that brighten a galaxy can also erode its future fuel supply. Metallicity changes the cooling curve, and the cooling curve shapes the entire star formation process. As metals appear, gas cools more efficiently, which can accelerate star formation and fragmentation. Fragmentation controls the masses of stars that form, and those masses control how much ultraviolet light is produced. In plain terms, chemistry influences starlight, and starlight changes chemistry. Dust changes radiative transfer, and radiative transfer controls what we infer from what we see. Dust can obscure ultraviolet light, re-radiate in infrared, and alter the inferred star formation rates. So, observers must separate intrinsic growth from observational bias, and that separation is subtle at high redshift. A dusty galaxy could look faint in ultraviolet, while a dust-poor galaxy looks unusually bright. JWST helps by sampling rest-frame optical light at high redshift, which is less sensitive to dust than ultraviolet. That improves stellar mass estimates and reduces reliance on ultraviolet alone. Rest-frame optical light also traces older stars more faithfully, so it can reveal whether a galaxy has been forming stars for tens of millions of years. At the edge of time, tens of millions is already a meaningful history. Spectroscopy also measures line ratios that trace ionization and metallicity, and those ratios are diagnostic. Those ratios test whether early galaxies are chemically primitive or already enriched. High ionization parameters can indicate intense radiation fields, while certain oxygen lines can hint at metallicity levels. Each ratio is a clue, and the clues must fit together. We connect these measurements to cosmological simulations, because simulations are our laboratories for unreachable epochs. Simulations predict halo, growth rates, star formation efficiency, and the scatter around those trends. They also predict diversity, because early galaxies are not a uniform class. Some should be quiescent, some bursty, and some temporarily quenched by feedback before reigniting. When observations find galaxies too massive too early, models must respond, and the response can take several forms. Either the efficiency is higher, the halos are rarer peaks, or assumptions need revision. Assumptions include the stellar initial mass function, the treatment of feedback, and the conversion between light and mass. Even small changes in those ingredients can shift the inferred pace of early assembly. We stress that tension is productive, not catastrophic, because it sharpens both sides of the comparison. It forces clearer accounting of selection effects, lensing magnification, and completeness limits. Gravitational lensing can boost apparent brightness, and it can do so without announcing itself loudly. A foreground mass can magnify a background galaxy, making it easier to detect and potentially misleading. Sometimes the lens is a visible cluster, and the distortion is obvious in arcs and stretched shapes. Other times the lens is subtle, a modest galaxy or group that quietly amplifies the background. Deep surveys, therefore, model foreground structures, and they do it with care because the correction matters. They check whether a candidate's brightness is intrinsic or amplified by an unseen lens. Another uncertainty is line identification at extreme redshift, because the spectrum can be sparse. A line could be misassigned, so teams seek multiple lines and consistent breaks. JWST's sensitivity makes those checks feasible, and feasibility changes the culture of claims. It can detect faint continua and weak lines that were unreachable, reducing the room for coincidence. We also clarify what we cannot yet do, even with the best instruments now flying. We cannot watch these galaxies evolve, so we infer histories from snapshots across redshift. That inference is statistical, and it depends on comparing many objects across cosmic time. We compare populations at different epochs, then reconstruct typical growth paths with models and simulations. The mysterious tone returns because the data are ancient but precise, and precision does not eliminate wonder. We are reading an autobiography written in photons that survived the entire age of the cosmos. Those photons crossed regions that were once neutral, then ionized, then structured into filaments and voids. They passed through gravitational potentials that bent their paths, and through dust that tried to erase them. We link back to the opening hook of the series, because the theme remains intact even at the edge of time. Points of light are only a fraction of what exists, yet here they carry the earliest chapters. We also link back to Chapter 3's engines, because even early galaxies may host compact power sources. Black holes may already be growing in these early systems, but their signatures can be subtle. Early accretion could contribute to ionizing budgets and heating, and it could shape local gas. Yet, distinguishing AGN from stellar processes requires line diagnostics and variability we rarely have. Some line ratios can hint at harder radiation fields, but starbursts in low metallicity environments can also produce hard spectra. The ambiguity is part of the challenge and part of the intrigue. So the central question sharpens again, and it becomes almost philosophical in its simplicity. How do galaxies reveal deep physics when their light is filtered by expansion and by intervening hydrogen? We summarize the observational ladder because the ladder is how we climb toward reliable claims. Imaging finds candidates by breaks. Photometry estimates redshift, and spectroscopy confirms with lines and continua. Each rung has failure modes, and each rung has its own kind of uncertainty. Each rung also adds constraints, turning a faint detection into a robust claim about cosmic time. GNZ11 showed the limits of the pre-Webb frontier, where single objects carried enormous weight. JD's GSZ14-0 shows what happens when the frontier becomes a surveyable landscape. The deeper implication is about structure formation speed, and speed is the hidden variable behind many debates. If mature features appear early, then the first halos and the first stars must ignite efficiently. That efficiency must be consistent with reionization constraints, which tie small galaxies to a cosmic transformation. Early galaxies must be numerous enough and leaky enough to ionize the intergalactic medium. Yet they must also survive feedback, because a galaxy that blows out all its gas cannot keep shining. They must keep enough gas to continue forming stars, even while winds and radiation try to shut them down. This is the same balance we saw later in starbursts, but now at smaller scales and earlier times, where the margins are thin. The coupling problem is primordial. We end by widening the frame, letting the camera pull back from a single faint source to the growing cosmic web. These first lights are seeds, but the universe does not stay small for long. Over billions of years, mergers, accretion, and feedback build giants, and the quiet early knots become sprawling systems. Disks grow, bulges form, black holes deepen, and radio structures ignite. Even the elements change because each generation of stars enriches the next, thickening the chemical palette. The early blue-white glare gives way to complex spectra, dust lanes, and structured halos. So we set up the final chapter's question, and we let it hang like a horizon line. How do these early seeds assemble into the largest galaxies and the most extended radio systems we know? We leave the edge of time with a final uncertainty that feels personal, because it touches our own origin story. If we can see the first galaxies, then the universe has been telling its story all along. Chapter 7 will follow that story forward. From first light to colossal structures, we ask how gravity and energy write the final pages. We leave the edge of time and move forward again, following the first lights into maturity. The early galaxies of Chapter 6 were seeds, compact and fragile, yet already shaped by dark halos. In deep field images, they appear as tight knots, blue-white, irregular, and crowded, because the young universe had little room for calm. Now we fast forward through billions of years, where the universe does its main construction work. Gravity keeps pulling, dark matter keeps merging, and baryons keep responding with cooling, star formation, and loss. The expansion of space continues in the background, yet local gravity still wins wherever matter becomes dense enough. Hierarchical growth becomes the pathway to giants, because small systems rarely stay separate forever. Halos accrete along filaments, merge at nodes, and deepen their potentials until the environment itself changes. In simulations, those filaments look like luminous threads of density, highways that guide matter into intersections where clusters eventually assemble. The central question returns with a new scale. How do galaxies form, transform, and reveal deep physics when the end products dwarf intuition? When the objects are this large, even definitions become slippery, because boundaries blur into shared halos and background light. We begin with the simplest rule that survives every chapter. Mass attracts mass, and time lets small asymmetries become large structures. A slight overdensity in the early universe becomes a halo. That halo becomes a group, and the group becomes a cluster with a central giant. In Chapter 1, collisions reshaped disks without most stars ever touching. Here, the same tidal physics repeats, but the bookkeeping is cumulative across thousands of encounters. The stars behave like a collisionless fluid, so gravity, not contact, does the sculpting, and the scars add up slowly. In Chapter 2, morphology looked diverse and almost artistic. Here, morphology becomes a record of assembly history, written into halos, envelopes, and quenched cores. A smooth elliptical is not simple at all. It is often the end state of repeated mixing that erased earlier patterns. In Chapter 3, black holes acted like engines and thermostats. Here, the engine's long-term duty cycle matters, because feedback can govern growth for billions of years. The question is not only whether an AGN turns on, but how often it returns, and how efficiently it couples to gas. In Chapter 4, starbursts regulated themselves through winds and supernovae. Here, those winds become one ingredient in keeping the biggest galaxies red and quiet. They preheat and expel gas early, and later they help prevent small satellites from delivering fresh, cold fuel. In Chapter 5, dark matter was the scaffold that made light optional. Here, the scaffold becomes a deep basin that collects galaxies, gas, and stripped stars. The basin is measurable through galaxy motions and lensing arcs, subtle distortions that betray mass where no light exists. We transition from early formation to late accumulation because the universe builds extremes by repetition. The giants are not born giant, they are assembled. Their size is a time-integrated outcome, the sum of many small additions, rather than a single dramatic birth. Our first giant is IC 1101, a supergiant elliptical often described as CD-like in structure. It sits where the cosmic web funnels matter into a rich cluster core. On screen, the cluster appears as a crowded city of galaxies, with IC 1101 like a pale, dominant glow at the center. Define the class clearly, because the label encodes physics. A CD galaxy is an enormous central elliptical with an extended diffuse stellar envelope. The C points to its central location, and the D hints at a diffuse component that can stretch far beyond a normal elliptical. That envelope is not a decorative halo, it is a merger archive. It forms through repeated accretion of satellites and the tidal stripping of their outer stars. Each infalling galaxy contributes its loosest stars first. Those are easiest to peel away during close passages. In a rich cluster, galaxies move fast and interact often, even when they do not fully merge. Each close passage peels stars away, adding to the central light. The process is sometimes called harassment, rapid, repeated encounters that heat stellar orbits and thicken structures. Dynamical friction does the slow work we met in Chapter 1, but on a grander stage. Massive satellites lose orbital energy to the dark halo and spiral inward. In plain terms, the satellite plows through a sea of dark matter and stars, raising a gravitational wake that drags it back. Over time, the cluster center becomes a sorting machine. Dense cores survive longer, diffuse outskirts are stripped early, and the central galaxy grows outward. What remains after many rounds is a dense inner body wrapped in a faint, sprawling shroud. IC 1101 represents the end state of that sorting, where the boundary of the galaxy becomes hard to define. The light profile fades gradually into the cluster background. If you stretch the contrast in an image, the galaxy seems to keep going, like fog that never quite ends. We explain effective radius because it is the practical ruler for these diffuse systems. The effective radius encloses half the total light, even when the outer halo is faint. It is a statistical boundary, and it depends on how carefully we measure the dim outskirts against the sky. For a supergiant elliptical, that radius can be enormous, implying stars spread across hundreds of thousands of light years. The galaxy's visible edge becomes a statistical choice. Astronomers fit surface brightness profiles, often Cercic-like curves, to infer how much light hides below the noise. The phrase "trillions of stars" needs translation into mass and luminosity. Stellar populations vary, but total stellar mass can reach tens of trillions of solar masses. That mass is dominated by long-lived, low-mass stars, which are numerous but faint, and therefore easy to underestimate. Luminosity does not scale simply with star count, because old stars are dimmer per unit mass. These giants shine with a red, evolved spectrum that signals long-quenched star formation. Their light is weighted toward cool giants and old main-sequence stars, so the color itself becomes a clock. Quenching connects back to feedback and environment. Hot intracluster gas prevents fresh cooling, and AGN heating can keep that gas from condensing. In clusters, much of the baryonic mass lives in X-ray, bright plasma at tens of millions of degrees, too hot to fall into stars quickly. The coupling problem from chapters 3 and 4 reappears in a calmer form. Energy injected into hot plasma can remain hot, making quenching stable over long times. When the gas is already thin and hot, a modest amount of heating can offset cooling, like a thermostat that never quite clicks off. Historically, this picture emerged as telescopes improved and clusters became laboratories. Early observers noticed that brightest cluster galaxies were unusually extended, and later photometry revealed their faint envelopes. X-ray astronomy then showed the surrounding intracluster medium, confirming that these giants live inside a much larger atmosphere. IC 1101 also forces a second definition, because some stars are no longer bound to any single galaxy. Intracluster light is made of stars without a home. It is so faint that it often appears only after careful stacking, deep exposures, and aggressive subtraction of background glow. Those stars were stripped during mergers, harassment, and tidal shocking in the cluster potential. They orbit the cluster itself, tracing its dark matter distribution. In motion, they behave less like a galaxy's halo and more like a diffuse stellar component of the cluster, responding to the cluster's overall gravity. Intracluster light becomes a visible map of invisible structure. It outlines where the cluster's gravity is deepest and where past interactions were most frequent. When we see streams and plumes in that light, ghostly arcs across the frame, we are watching the aftermath of disruption. This is where the dark matter scaffold becomes tangible again. The central galaxy sits at the bottom of a deep potential well, dominated by the cluster halo. Lensing reconstructions often show the same center, aligning the brightest galaxy with the peak of the mass map, close, but not always perfectly. The galaxy's own dark halo is real, but the cluster's halo is the main container. The brightest galaxy is not the most massive component, it is the most visible one. Most of the cluster's baryons are not stars at all, but hot gas that glows in X-rays and carries the chemical fingerprints of past supernovae. We connect this to Chapter 5's lesson about light as a biased tracer. In clusters, the bias is extreme because most baryons are hot gas and most mass is dark. The stars are the glitter on a much larger structure, and the glitter can mislead if we forget the hidden bulk. So IC 1101 is not only a giant galaxy, it is a boundary between categories. It is a galaxy embedded in a cluster, and its outer stars blend into the cluster's shared light. At some radius, the question, "Where does the galaxy end?" becomes the question, "Where does the cluster begin?" We pause to state what this means for hierarchical growth. The biggest galaxies grow late by cannibalism, while their stars can be old because the growth is mostly dry mergers. The stars formed earlier in smaller systems, then were assembled later into one enormous body. Growth without youth. Dry mergers are mergers with little cold gas, so they add stars without igniting new ones. They puff up sizes, build envelopes, and preserve red colors. Because orbital energy must go somewhere, the remnant expands, and the effective radius can grow faster than the stellar mass. That resolves one tension from Chapter 1 about post-merger fate. Gas-rich mergers can rebuild disks and trigger bursts, but gas-poor mergers build spheroids and halos. The same gravitational choreography plays out, yet the presence or absence of cold gas decides whether the aftermath is blue and bright or red and quiet. Environment decides which path dominates, because clusters strip gas and heat reservoirs. The same collision physics yields different outcomes when the fuel supply changes. Ram pressure from the intracluster medium can sweep gas out of infalling galaxies, like wind tearing leaves from a branch before they ever reach the center. Now we scale upward again, from stellar envelopes to structures that are not made of stars at all. We shift from optical giants to radio giants. The visuals change with the wavelength, and the universe reveals a second kind of enormity, one drawn in magnetic fields and relativistic particles. Alcyonius is a giant radio galaxy whose lobes extend for millions of light-years. It is a galaxy-scale engine riding on intergalactic space. In radio maps, the host can be a small point, while the lobes bloom outward like faint wings that dwarf the visible galaxy. We define the phenomenon in physical terms. A radio galaxy is powered by an active nucleus that launches relativistic jets from near a supermassive black hole. Close to the event horizon, magnetic fields thread the accretion flow, and rotation helps collimate energy into narrow beams. Jets carry energy, momentum, magnetic fields, and cosmic rays far beyond the host. Where they terminate, they inflate lobes that glow in radio synchrotron emission. At the hot spots, shocks accelerate particles again, replenishing electrons that would otherwise fade as they radiate away energy. Synchrotron emission is produced when relativistic electrons spiral in magnetic fields. It turns invisible particle acceleration into a measurable spectrum and morphology. The spectrum steepens as electrons age, so radio color can act like a timeline, revealing where particles were energized most recently. We connect this to Chapter 3's engines, because the core mechanism is the same. Accretion onto a black hole taps gravitational energy and collimates it into jets. A small amount of mass falling deep into a potential well can power structures that reach far beyond the galaxy's own stars. M87 and Centaurus A were earlier examples of the engine in nearby, readable detail. Alcyonius is the same engine scaled to an extreme lifetime and reach. It asks a simple, unsettling question: how long can an engine run, and how far can its signature travel through near-empty space? The lobes of Alcyonius trace long-lived AGN activity, not a brief flare. Their size implies sustained power and a surrounding medium that does not choke expansion. Even at near light speeds, a jet needs immense time to inflate lobes across millions of light years, and that time must be available. We explain why some jets grow so large, because size is not only power. The intergalactic environment sets resistance, and low density allows lobes to expand farther. In denser regions, ram pressure and turbulence bend jets, disrupt them, and drain their momentum into the surrounding gas. A sparse medium reduces radiative losses and ram pressure confinement. The lobes can remain coherent while they push into the cosmic web's tenuous gas. In that thin plasma, magnetic pressure and relativistic particles can dominate the lobe interior, allowing it to behave like a buoyant bubble. Sustained fueling is the second requirement, because jets need time. The black hole must keep accreting, often through slow inflow, minor mergers, or cooling from hot halos. The fueling can be intermittent, on, off, on again. Yet the lobes integrate that history into one extended structure. Magnetic field structure and cosmic ray transport shape the lobe's stability and brightness. Fields guide particles, and turbulence can reaccelerate them over long distances. The result is a living plasma, where shocks, shear, and instabilities compete to either preserve the lobe or shred it into filaments. We keep the coupling problem in view because jets must couple to their surroundings to matter. Shocks, bubbles, and mixing transfer energy into the circumgalactic and intergalactic medium. Even when the jet is narrow, its influence can be wide because the lobes displace gas and drive sound waves through it. In clusters, that coupling can prevent cooling flows and regulate the central galaxy's growth. In filaments and groups, it can heat gas and alter future accretion. Heating does not need to be dramatic. A small temperature increase can lengthen cooling times enough to change what gas will do over billions of years. So, the radio giant is not only a spectacle, it is feedback on the largest accessible scales. It is a galaxy influencing the thermal history of its neighborhood. The lobes become a kind of archaeological layer in the intergalactic medium, recording where energy was deposited and when. We place Alcyonius in the cosmic web context because no giant evolves alone. Filaments feed halos, nodes host clusters, and voids limit interactions. When the camera pulls back to the full web, the lobes look like annotations in the margins, signals written onto the same structure that feeds galaxies. Radio morphology reflects that context. Jets can bend, disrupt, or remain straight depending on density gradients, bulk flows, and the motion of the host. A moving galaxy can leave its jets swept back, and a changing environment can make one lobe brighter as it pushes into denser gas. The web also explains why extremes are rare. To grow a supergiant elliptical, you need a rich node, but to grow a giant radio source, you often need low density. The requirements are almost opposite, which is why the sky does not fill with both kinds of giants in the same places. That apparent contradiction is a clue, not a problem. Different kinds of giants occupy different niches in the same cosmic network. The universe does not make one kind of extreme. It makes many, each tuned to a particular balance of supply, resistance, and time. IC 1101 is a giant built by accumulation at a crowded node. Alcyonius is a giant built by an engine expanding into relatively open intergalactic space. One is mostly starlight spread thin, and the other is mostly plasma, and fields made visible only by radio waves. Both giants still depend on the same ingredients we have followed all series. Gravity assembles mass, mergers rearrange it, feedback redistributes energy, and dark matter sets the stage. The differences are in emphasis. How much is assembled by collision, and how much is reshaped by energy injection. Now we synthesize the arc across all chapters in one continuous story. The universe begins with tiny fluctuations. Then dark matter collapses into halos and filaments. Those fluctuations were measured in the cosmic microwave background, and their faint pattern became the blueprint for every later structure. Gas falls into those halos, cools, and forms the first stars and galaxies, as we saw at the edge of time. Ionization and early feedback set the first constraints. Ultraviolet light from early stars and quasars heated intergalactic hydrogen, changing how easily gas could collapse into the smallest halos. As time passes, halos merge and accrete, and galaxies collide as Chapter 1 established. Tides reshape orbits, and dynamical friction turns encounters into unions. The rate of merging declines with time, yet the biggest systems keep growing because they sit where the traffic is heaviest. Out of that violence, structures emerge that look stable. As Chapter 2 emphasized, bars, rings, and bulges become channels and signatures of internal evolution. Even in quiet phases, stars migrate, gas flows inward, and angular momentum is redistributed, slow processes that still leave visible architecture. Those channels can feed central black holes, igniting AGN phases like Chapter 3. Jets and winds then regulate gas, sometimes quenching, sometimes triggering new cycles. The same outflow that heats one region can compress another, so feedback is not a single outcome, but a range of possibilities. Starbursts and stellar winds add a second regulatory loop, as Chapter 4 showed. They enrich gas, drive fountains, and set the efficiency of turning baryons into stars. Metals increase radiative cooling, yet winds can remove the very gas that would cool, so the net effect depends on depth of the potential well. All of it occurs inside dark matter potentials that dominate the mass budget, as Chapter 5 made unavoidable. Light traces only a fraction, but motion and lensing reveal the rest. When we measure velocity dispersions in giant ellipticals, we are weighing the combined pull of stars, gas, and an even larger dark component. The first galaxies in Chapter 6 were not isolated miracles, but early steps in that same hierarchy. Their compactness and rapid growth were the beginning of a long assembly. They were denser because the universe itself was denser, and because their gas fractions were higher, making star formation efficient and intense. IC 1101 and Alcyonius are the late chapters written at the largest scales. They show what happens when the same rules are allowed to run for cosmic time. They also show that largest can mean different things, largest in stellar extent or largest in energetic reach. We answer the central question in the only honest way a documentary can. Galaxies form by gravity and dark halos, transform by mergers and internal dynamics, and reveal physics through measurable signatures. Their shapes, colors, and motions are not decoration, but data, encoded consequences of forces we can model. They reveal black holes through jets and ionized gas, dark matter through motions and lensing, and cosmic history through redshift and population statistics. They are laboratories built by nature. When we compare many galaxies across time, we turn the sky into an experiment with billions of trials. The finale also reframes the opening hook about points of light being a tiny fraction. The fraction is small, yet it is structured, and structure is readable. The faintest halo light and the widest radio lobes both tell us that the universe keeps records, even when the ink is almost invisible. A giant elliptical tells us about merger rates, stripping, and cluster potentials. A giant radio galaxy tells us about accretion physics, magnetized plasmas, and the intergalactic medium. Together, they ask a deeper question. How does the same gravity produce both quiet, red relics, and violent, far-reaching outflows? Even intracluster light, the stars without a home, becomes a paragraph in the autobiography. It records interactions that no single snapshot could show. If we could watch the cluster over time, those stars would appear as streams that dissolve, gradually turning sharp events into a smooth glow. We return to human scale without pretending the scale is comfortable. Our bodies are tuned for meters and minutes, but our instruments extend those senses. We build mirrors, antennas, and detectors that translate ancient photons into patterns we can interpret. And we learn to trust measurements that defy intuition. Light is the messenger that brings the past into the present. Gravity is the map that lets us weigh what we cannot see. When we combine them, spectra for composition, imaging for structure, dynamics for mass, we turn distant objects into physical systems rather than distant ornaments. Time is the final dimension of the journey, because every galaxy is a history compressed into a shape. When we measure that shape, we decode the forces that wrote it. The question is never only, what is it? But, what sequence of events could have produced it? And what does that imply about the unseen matter around it? The universe remains mysterious, but it is not arbitrary. The largest giants still follow comprehensible laws, and those laws connect the smallest seeds to the widest lobes. The cosmic web ties the story together, filaments feeding growth, nodes amplifying encounters, and voids providing the quiet that lets some jets run free. So the journey ends where it began, with the promise that the sky is legible. Galaxies are the universe's autobiography, and we have learned to read its pages. The letters are written in starlight and radio waves, and the grammar is gravity, thermodynamics, and time. We are small, but the cosmos is knowable in fragments that add up. In every merger remnant and radio lobe, the same physics speaks in a different accent. And as we look at these giants, diffuse, immense, and patient, we are forced to ask what other extremes still wait, hidden in plain sight. Across this journey, we learned that galaxies only look still, because their true clocks tick in hundreds of millions of years. In collisions like the antennae and the mice, gravity does the cutting without direct impact. Tides draw out tails, gas shocks into starbursts, and dark halos quietly set the pace of the dance. From that wreckage, calmer structures emerge. Rings, bars, warps, dust lanes, and asymmetries. Each one a fossil clue, showing how angular momentum moved, where gas piled up, and which histories were erased or preserved. Then we listened for the engines hiding inside the architecture. Some galaxies ignite their centers, feeding black holes that answer with jets and winds, a thermostat that can heat, stir, or evacuate the very fuel that made it flare. Others burn from the outside in, where clustered supernovae and radiation pressure drive galaxy-scale winds, sometimes competing with an active nucleus, sometimes handing off control as conditions change across cosmic time. And underneath both kinds of violence, whether it ends in quenching, recycling fountains or renewed inflow, lies the coupling problem, the still murky physics of how energy finds leverage in cold, clumpy gas. When the light dimmed, the evidence did not disappear. It simply changed languages. Ghostly galaxies and faint outskirts taught us to read motion, lensing, and hot gas instead of starlight. and to accept that most of a galaxy's mass is an unseen scaffold. At the edge of time, the first compact galaxies showed that the rules were already in place early, even when the universe was young, crowded, and turbulent. And in the cosmic giants, brightest cluster galaxies with envelopes that blur into intracluster light, and radio behemoths whose lobes outlive their fuel, we saw the same hierarchy of gravity produce opposite extremes, depending on environment, supply, and the long duty cycle of the central engine. Yet the story never collapses into a single ending, and that is one of its deepest revelations. Some mergers build ellipticals, some rebuild disks, some trigger brief starbursts or long AGN phases, and some barely leave a scar, because outcomes hinge on gas content, mass ratio, orbital geometry, and the architecture of the dark halo. The universe is not hiding randomness in the details. It is hiding conditional rules, thresholds, timescales, and feedback loops that we can test by reading structure as evidence. Every tail, every color gradient, every rotation curve, every bubble in hot gas is a sentence in that autobiography, written in gravity and edited by light. In the end, our chapters connected into one method as much as one narrative. We began with debris and tides, moved through beauty that channels matter, confronted engines that regulate growth, traced winds that redistribute metals, followed the missing light to missing mass, watched the first galaxies ignite, and finally stood among giants where a galaxy's boundary becomes a question. The mystery remained, but it sharpened, because the same physics kept reappearing in new disguises: orbital energy, angular momentum, cooling, turbulence, and the patient pull of dark matter. If galaxies are the grandest structures we can still read, then the act of reading them is how the cosmos becomes comprehensible. And that comprehension does not require certainty about every mechanism, only honesty about what the evidence says. We do not yet know exactly how jets couple to multi-phase gas, or how long a black hole can sustain lobes the size of superclusters, or where a CD envelope truly ends and a cluster begins. We do not yet know how often the engine turns on, what fraction of galaxies cycle through it, or when stellar feedback dominates and when it yields to an accreting horizon. But we do know this much, because the sky keeps repeating it in different forms. Galaxies change, and the way they change is governed, not arbitrary. Their shapes are not decorations, they are records. So the journey to all galaxies becomes less like a catalog and more like learning a script the universe keeps revising. Rings and bars are not the opposite of collisions. They are often the aftermath, the settled mathematics of past disruption. Quiet red giants and violent radio monsters are not contradictions. They are outcomes of the same hierarchy, tuned by where the galaxy lives in the cosmic web and what fuel arrives and how feedback closes the loop. The deeper we look, the more the cosmos seems to insist on a paradox that is almost comforting. Its largest structures are built by invisible matter, yet their visible scars remain legible. That is the thread tying every chapter together. Galaxies are not just places where stars live. They are experiments running for billions of years, with initial conditions set near the Big Bang. When we read their structure, color, motion, morphology, we are not merely describing them, we are extracting the physics that shaped them. The universe does keep secrets, but it keeps them in public, in the geometry of tidal tails, in the temperature of shocked gas, in the emptiness where stars should be, and in the faintest photons that have traveled since the first dawn. To understand galaxies is to understand how the cosmos writes, edits, and sometimes erases its own past. And if there is closure here, it is not the end of the story, but the end of our illusion that the story is unreadable. We have watched gravity sculpt order from chaos, watched feedback prevent simple growth, and watched dark matter hold the whole narrative together without ever stepping into the light. We have seen that formation is rarely a single event, and transformation is rarely a single cause, but the evidence always accumulates in the same places, edges, centers, and the spaces between. The autobiography is vast, but it is coherent, and each new observation sharpens the grammar. So, when we return to the opening claim that every star you've ever seen is a decoy, we can finally say what it was really pointing toward. The stars are not a lie. They are the ink, and the decoy is the comfort of thinking ink is the whole book. Behind the glittering veil, galaxies crash and cannibalize. Yes, but they also remember, and their memories reveal the deepest physics we have. Dark matter's scaffold, black holes' engines, and the first light after the Big Bang. The wreckage is not just destruction, it is evidence. And the question that launched us, what happens when we journey to every kind of galaxy and read the true physics of everything in their shadows, now has an answer that is also a challenge. What happens is that the universe stops feeling like a collection of objects and starts feeling like a set of laws made visible, repeated across time, scale, and environment. We do not reach a final map of every mechanism, but we do learn how to keep reading and how to tell which mysteries are shrinking. In a cosmos where so much is unseen, galaxies remain our most faithful translators. Because in the end, galaxies are the universe's autobiography, written in gravity and light, revised by collisions, and proofread by feedback. All of it bound to an invisible scaffold. The largest structures still follow comprehensible rules, and that fact is as mysterious as it is beautiful. If the universe can be read at all, it is because it chose to leave its equations scattered across the sky in forms we can learn to recognize. So keep looking and keep asking what a shape is trying to tell you, because every new survey and every deeper image is another page recovered from cosmic time. When we journeyed through every kind of galaxy, the wreckage did not just show violence. It revealed a readable physics, from dark matter's scaffold to black hole engines and the first light. The stars were never the whole story. They were the ink, and the galaxies were the pages where the universe wrote its laws in public. Galaxies are the universe's autobiography. Gravity writes the plot, light reveals the edits, and time turns collisions into meaning. If you want to know what reality is made of, you don't look past galaxies. You learn to read them. The next time you see a faint smudge in the night sky, follow it deeper and let its shape ask you what history you're willing to uncover.